For most of human history, distance has been an obstacle that eventually surrendered. An ocean could be crossed, a mountain range could be passed, a continent could be mapped. Even the empty space between Earth and the Moon, once seemingly unreachable, eventually became a journey measured in days. It is therefore natural to extend this pattern outward. If humanity survived long enough, improved its machines, and learned to travel faster, then perhaps the planets would become stepping stones. Beyond them would lie the edge of the solar system, and beyond that edge, the stars. The assumption is comforting because it agrees with nearly everything our history has taught us. Technology improves, journeys become shorter, frontiers retreat, but the space beyond the planets does not behave like the frontiers humanity has crossed before. The difficulty is not simply that the next destination is farther away. The difficulty is that distance itself begins to change the nature of the journey. Our fastest machines have already demonstrated something remarkable. Human technology can reach the outer planets. It can survive beyond them. It can continue transmitting information from regions where the sun has become little more than the brightest star in a dark sky. Voyager 1 has travelled farther from Earth than any other human-made object. Launched in 1977, it passed Jupiter and Saturn before continuing outward on a trajectory that would never bring it home, decades later. Its journey carried it through a boundary known as the heliopause, where the outward influence of the solar wind encounters the surrounding interstellar medium. In one important sense, Voyager entered interstellar space, and yet Voyager has not truly escaped the solar system. That apparent contradiction reveals the first problem with the familiar picture. There is no single, universally agreed wall surrounding the sun. The solar system has several possible edges, depending on what we mean by belonging to the sun. If we mean the region dominated by the solar wind, Voyager has already crossed its boundary. If we mean the region containing the familiar planets, then the boundary lies much closer. But if we mean the region where objects can remain gravitationally associated with the sun, the solar system may stretch enormously farther, potentially into the distant reservoir of icy bodies usually called the Oort cloud. The difference is immense. Voyager's achievement is extraordinary, but measured against the possible scale of the sun's distant gravitational domain, its journey has barely begun. And beyond even that distant frontier waits a much larger emptiness. The nearest known star system to our own is Alpha Centauri, a little more than 4 light-years away. That sounds almost modest when astronomy routinely discusses galaxies millions or billions of light-years distant. But a light-year is not a unit designed around human experience. It is the distance light travels through vacuum during 1 year. Light can circle Earth more than 7 times in a single second. Allow it to continue at that speed for an entire year, and it travels roughly 9.46 trillion kilometers. Alpha Centauri lies more than 4 such distances away. At the velocities achieved by spacecraft such as Voyager, an interstellar journey would not take decades. It would take tens of thousands of years. This is where the old pattern of exploration begins to weaken. The Pacific Ocean was vast, but crossing it did not require a civilization to survive inside a ship for thousands of generations. The Moon was distant, but astronauts could carry the supplies required for their journey. Mars is vastly harder, yet communication with Earth still occurs on timescales measured in minutes rather than years. Interstellar distance belongs to another category. A spacecraft traveling between stars would eventually move through a region where Earth could provide almost nothing immediately. A request for help could take years to arrive. The answer would require years to return. There would be no rapid rescue mission. No replacement component could simply be launched after a failure. And for a sufficiently long journey, the people who designed the spacecraft might have been gone for centuries before it approached its destination. Speed appears to offer the obvious solution. Travel fast enough and the distance becomes manageable. But speed carries its own price. A spacecraft must somehow acquire enormous kinetic energy. It must manage the heat produced by its systems. It must survive radiation. It must avoid or withstand collisions with particles and dust. If it intends to stop at another star rather than merely pass through, it must also lose much of the velocity that was so difficult to gain. For robotic probes, these are formidable engineering problems. For human beings, they are only the beginning. Humans cannot simply be switched off during a voyage. We require a remarkably narrow range of environmental conditions. We need oxygen at appropriate pressures, drinkable water, food containing particular nutrients, protection from radiation, controlled temperatures, waste processing, medical care, and some method of maintaining physical health in an environment very different from Earth's surface. A voyage lasting centuries would require something even more difficult. It would require continuity. The spacecraft would need to function not merely as transportation but as habitat, ecosystem, hospital, community, archive, workshop, and perhaps eventually as an independent civilization. This is why the question of escaping the solar system cannot be reduced to rocket performance. The problem quietly expands until it touches physics, biology, ecology, engineering, psychology, sociology, and time itself. And there is another complication. The phrase, humans will never escape the solar system, sounds like a prediction. Science is rarely comfortable with predictions about what intelligent beings will never accomplish. Technologies that appear impossible in one century can become ordinary in another. There is no known law of nature stating that a human being must remain gravitationally bound to the sun forever. A sufficiently energetic trajectory can leave. Spacecraft are already following such trajectories. The deeper question is therefore not whether escape violates physics. It does not. The question is whether a living human civilization can bridge the enormous gulf between stars while remaining recognizably human, and whether the technologies required to do so can ever become practical rather than merely permissible. That distinction will accompany us throughout this journey. Possible is not the same as achievable. Achievable is not the same as sustainable. And sustainable is not necessarily the same as desirable. Before considering engines powerful enough to cross interstellar distances, there is a quieter problem we must solve first. We need to know what we are trying to escape. The familiar diagram of the solar system usually ends somewhere beyond Neptune, perhaps with Pluto and a scattering of icy worlds beyond it. Nature does not. Far outside the planetary region, the Sun continues to shape space in several different ways, creating boundaries that do not coincide with one another. Some have already been crossed by our spacecraft. Others remain so distant that no human-made object will approach them for thousands of years. And depending on which boundary we choose, humanity may already have touched interstellar space while still remaining extraordinarily deep inside the greater territory of the Sun. So before asking how we might leave our cosmic home, we must first confront a surprisingly difficult question. Where, exactly, does the solar system end? There is something reassuring about a border. A coastline tells us where land ends and ocean begins. The atmosphere thins gradually. Yet we can still define useful boundaries between Earth and space, even nations, despite the complexity of geography and politics, can usually be drawn as lines on a map. The solar system offers no such simplicity. Look at a diagram in a textbook and its architecture appears almost orderly. The Sun sits at the centre. Mercury, Venus, Earth, and Mars circle close by. Beyond them lies the realm of the giant planets. Neptune marks the outermost major planetary orbit, while Pluto and thousands of smaller icy bodies occupy the distant regions beyond. It is tempting to look at this arrangement and place the edge somewhere after the last planet, but Neptune is not a border. At an average distance of roughly 30 astronomical units from the Sun, it is simply the most distant of the 8 recognized planets. An astronomical unit, or AU, is approximately the average distance between Earth and the Sun, about 150 million kilometers. Neptune therefore circles the Sun roughly 30 times farther away than Earth does. That is already an enormous distance. Light leaving the Sun reaches Earth in a little over 8 minutes. Reaching Neptune takes about 4 hours. Yet beyond Neptune, the solar system continues. The first hint of this larger architecture is the Kuiper Belt. This broad region contains countless icy bodies left over from the formation of the planetary system. Pluto is one of its most famous inhabitants. Although the structure itself extends across billions of kilometers, objects here orbit the Sun just as Earth and Neptune do, but their world is colder, darker, and far more sparsely populated. The Sun still dominates their motion. Travel farther, however, and the architecture becomes less familiar. Some objects occupy highly elongated orbits that carry them enormous distances from the Sun. Sedna is a particularly intriguing example. Its orbit reaches far beyond the main Kuiper belt, suggesting that the outer solar system may contain populations of bodies that are difficult to detect from Earth. And still, we have not reached the most distant suspected structure. Far beyond the known planets may lie the Oort cloud. Unlike the relatively flattened arrangement of the planets and Kuiper belt, the Oort cloud is thought to form an enormous, roughly spherical reservoir of icy objects surrounding the solar system. We have never photographed the Oort cloud as a structure. Its existence is inferred largely from the behavior of long-period comets that arrive in the inner solar system from extremely distant orbits. These comets appear to have spent most of their histories far beyond the planets. The outer extent of the Oort cloud is uncertain. Estimates can reach tens of thousands of astronomical units and perhaps around 100,000 AU in some descriptions of its most distant reaches. At those scales, something remarkable happens. The distance to the edge of the Sun's extended comet reservoir becomes a meaningful fraction of the distance to neighbouring stars. The solar system no longer resembles a compact collection of planets surrounded by empty interstellar space. Instead, the Sun occupies a vast and diffuse gravitational territory whose outskirts may overlap dynamically with the wider environment of the Milky Way. But gravity provides only one possible definition of the solar system. There is another boundary much closer to us. The Sun constantly releases a stream of charged particles known as the solar wind. Near Earth, this wind can interact with our planet's magnetic field, contributing to phenomena such as auroras, but it does not stop at Earth. It flows outward past Mars, past Jupiter, past Saturn, Uranus and Neptune. As it expands, the solar wind creates an enormous bubble around the Sun called the heliosphere. This bubble moves through the surrounding interstellar medium as the Sun travels around the Milky Way. Eventually, the outward solar wind encounters the material between the stars. The transition is complicated rather than perfectly sharp. But one boundary is particularly important. The heliopause marks the region where the solar wind's outward pressure is balanced by the surrounding interstellar environment. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed it in 2018. Measurements from their instruments revealed changes in charged particles, magnetic conditions, and plasma that indicated the spacecraft had entered the local interstellar medium. Humanity had placed functioning machines beyond the heliosphere. If the heliopause defines the edge of the solar system, then our machines have escaped. But consider the strange result. Voyager 1 crossed that boundary at a distance of roughly 120 AU from the Sun. The hypothetical Oort cloud may extend hundreds of times farther, so a spacecraft can enter interstellar space while remaining within a much larger population of objects gravitationally associated with the Sun. Both statements can be true. The apparent contradiction exists because the solar system is not a single physical object with a hard outer surface. It is several overlapping domains. There is the planetary system. There is the region populated by smaller orbiting bodies. There is the heliosphere created by the solar wind. There is the much larger gravitational environment in which distant comets may remain loosely attached to the Sun. And even gravity does not provide a perfectly isolated kingdom. Far enough from the Sun, the gravitational influence of the Milky Way and passing stars becomes increasingly important. Over immense periods, these external forces can disturb distant cometary orbits. The outer solar system is therefore not a wall. It is a fading relationship. The farther we travel from the Sun, the weaker its light becomes. Its solar wind eventually gives way to interstellar plasma. Its gravitational dominance gradually competes with other influences. The Sun does not suddenly release its surroundings at one particular distance. Its presence simply becomes less decisive. This matters because the meaning of escape depends entirely on which relationship we choose. A spacecraft can escape the Sun gravitationally if it has enough energy to follow an unbound trajectory. Several human-made spacecraft already do. Pioneer 10 and Pioneer 11 are leaving the planetary system. Voyager 1 and Voyager 2 are doing the same. New Horizons, after its encounter with Pluto and the Kuiper belt object Arrokoth, is also travelling outward on an escape trajectory. None will orbit the Sun forever. In that technical sense, escape is not hypothetical. We have already done it with machines. But these spacecraft expose a second distinction. Leaving is not the same as arriving. A bottle released into an ocean may drift away from shore. but that does not make it capable of crossing the ocean deliberately, reaching a chosen harbour, slowing down, and sustaining living passengers along the way. Our outward-bound probes are more like messages cast into the cosmic current. They are not interstellar transport systems. Their velocities become almost painfully small when compared with the scale separating the stars. And this brings us to a deeper reason the boundary matters. If we define escape as merely crossing the heliopause, humanity could conceivably send people beyond it with sufficiently ambitious extensions of technologies we already understand. The distance is enormous, but not fundamentally interstellar. If instead we mean leaving the sun behind and becoming a civilization capable of reaching another star, the problem transforms. Between the outermost regions of the sun's domain and the nearest neighbouring system lies a gulf with almost nothing resembling the stepping stones that supported earlier human exploration. No islands, no convenient planets, no nearby ports, only a thin interstellar medium extending across trillions upon trillions of kilometres. To understand whether humans can cross that gulf, we must first understand the enormous structure from which we would depart, because the solar system we carry in our minds, with its neat rings of planets around a bright central star, represents only its illuminated inner rooms. Beyond Neptune, the house continues into darkness, and its most distant walls may lie farther away than any spacecraft has yet travelled by orders of magnitude. The solar system is usually drawn as a family portrait. 8 planets occupy neat paths around the sun. The rocky worlds gather near the centre. The giant planets stand farther away. Beyond Neptune, Pluto sometimes appears near the edge of the page, followed by darkness. The picture is useful, but it is not remotely to scale. If the sun were reduced to something small enough to hold in your hand, the planets would not form a compact arrangement around it. They would be scattered across an enormous volume of mostly empty space, and the structures beyond Neptune would extend so far that the familiar planetary system would begin to seem like a small central district inside a much larger territory. This architecture began taking shape roughly 4.6 billion years ago. The young sun formed within a collapsing cloud of gas and dust. Around it, material settled into a rotating disk. Tiny grains collided and accumulated. Larger bodies emerged. Some became planets. Others became moons, asteroids, comets, or fragments that would never grow into major worlds. Much of the early solar system was eventually cleared, absorbed, scattered, or rearranged. But not all of it disappeared. Its surviving remnants form a kind of archaeological record. Closest to the sun are the terrestrial planets. Mercury, Venus, Earth, and Mars occupy a relatively small region compared with what lies beyond. Their compositions reflect conditions in the warmer inner protoplanetary disk, where rocky and metallic materials could survive more easily than volatile ices. Then comes the asteroid belt. Popular images sometimes depict it as a crowded obstacle course, but the real asteroid belt is extraordinarily sparse. A spacecraft can cross it without weaving between rocks. Beyond it begins the domain of the giant planets. Jupiter dominates this region gravitationally, Saturn follows. Then Uranus and Neptune circle in the colder outer reaches. Neptune's orbit lies around 30 AU from the Sun. For much of the 20th century, the space beyond seemed comparatively mysterious. Pluto had been discovered in 1930, but it appeared to be an isolated curiosity. That picture did not survive. Beginning in the late 20th century, astronomers discovered increasing numbers of icy objects beyond Neptune. What had looked like an almost empty frontier revealed itself as a broad population. The Kuiper Belt had entered observational astronomy. Its existence transformed Pluto's identity. Pluto was no longer simply a peculiar object at the edge of the known system. It belonged to a larger family of distant icy worlds, including bodies such as Haumea, Makemake, and many smaller objects. The Kuiper Belt is not merely debris scattered randomly beyond Neptune. Its structure contains traces of the solar system's early evolution. Some objects occupy orbital resonances with Neptune. Pluto, for example, completes 2 orbits around the Sun for every 3 completed by Neptune. This relationship prevents close encounters despite the geometry of their paths. Other populations have different orbital histories. suggesting that the giant planets themselves may have migrated during the solar system's youth. This is an important idea. The planets may not have formed exactly where we see them today. Models of early solar system evolution indicate that gravitational interactions among the giant planets and smaller bodies could have shifted planetary orbits, scattering enormous numbers of icy objects in the process. Some were thrown inward, some were expelled from the solar system entirely, others were pushed onto distant orbits. The quiet outer system we observe today may therefore be the aftermath of an ancient gravitational rearrangement. Beyond the main Kuiper belt lies the scattered disk. Objects here often travel along more eccentric and inclined paths, reaching much farther from the Sun. Neptune's gravity has played an important role in shaping many of these orbits, but then we encounter bodies that become harder to explain. Sedna never comes particularly close to Neptune. Its orbit carries it from roughly 76 AU at its closest approach to the Sun to many hundreds of AU at its farthest. That makes ordinary interactions with Neptune an incomplete explanation for its present orbit. Something else may have influenced it. Perhaps the young Sun formed in a cluster where neighbouring stars passed much closer than stars do today. A stellar encounter could have disturbed distant objects. Other hypotheses have been considered as astronomers try to understand the orbital architecture of extreme trans-Neptunian bodies. Some researchers have explored whether an undiscovered distant planet could influence certain observed orbital patterns. The proposed object is often called Planet 9. It remains hypothetical. No such planet has been directly detected, and scientists continue to debate whether the observed patterns require a planet at all, or could arise from observational biases and other effects. This is an example of how quickly certainty fades in the distant solar system. Near Earth, planets can be studied in exquisite detail. Far beyond Neptune, astronomers may struggle even to discover objects hundreds of kilometers across. Sunlight becomes weak. Orbital periods become enormous. A distant body can move so slowly against the background stars that years of observations may reveal only a small portion of its path. And then, beyond these scattered populations, the map becomes even less certain. The Oort cloud is thought to begin perhaps thousands of astronomical units from the Sun, though its exact structure and boundaries are not directly known. Its inhabitants would receive extraordinarily little sunlight. From such distances, the planetary system would collapse visually toward the Sun, Jupiter, Saturn, Earth, and the other planets would occupy a tiny region around a distant point of light. Yet even there, the Sun's gravity could still matter. Long-period comets provide the strongest evidence for this remote reservoir. Some arrive in the inner solar system on trajectories indicating that they have fallen inward from enormous distances. A passing star or the gravitational influence of the galaxy can slightly alter a distant comet's orbit. A tiny disturbance, acting on an object barely bound to the Sun, may eventually send it falling inward. Thousands or millions of years later, that object can appear near the planets as a bright comet. In this way, events occurring near the gravitational outskirts of the solar system can eventually become visible from Earth. The scale is difficult to absorb. Voyager 1 has spent nearly half a century travelling outward, yet reaching the inner regions commonly associated with the Oort cloud would take it centuries. Crossing the broader cloud could take tens of thousands of years. Long before that journey ended, the spacecraft would fall silent. Its electrical power would fade. Its instruments would cease operating. It would continue moving, but no longer as an active explorer. It would become an artifact. The solar system therefore contains several layers of increasingly tenuous connection. The planets form its bright central architecture. The Kuiper belt preserves an icy outer population. The scattered disk stretches the known architecture farther. Extreme distant objects hint at histories we do not fully understand. And the Oort cloud may surround everything like a nearly invisible halo. But there is another structure that does not consist of planets, comets, or asteroids at all. It is formed by the Sun itself. Every second, the Sun sends charged particles streaming outward into space. These particles flow past every planet and continue far beyond Neptune, carrying the influence of our star into the darkness. To understand where the solar system meets the galaxy, we must follow that invisible wind, and its existence was once far from obvious. Long before spacecraft could travel beyond the planets, astronomers already knew that something was moving outward from the Sun. The evidence arrived in one of the oldest visitors humanity had ever watched crossing the sky: comets, when a comet approaches the sun. Frozen material on its surface begins to release gas and dust. A glowing atmosphere forms around the nucleus, and immense tails can stretch across millions of kilometers. For centuries, those tails were treated mainly as beautiful celestial features, but they contained a clue. One part of a comet's tail tends to point away from the sun, not behind the comet in the ordinary sense of an object moving through air, but away from the sun itself. Radiation pressure could explain part of this behavior, particularly the dust tail. Yet another component, made of ionized gas, suggested that something else was interacting with the comet. By the middle of the 20th century, pieces of the puzzle were accumulating. The sun's outer atmosphere, the corona, was known to be extraordinarily hot during a total solar eclipse. The corona appears as a pale structure extending outward around the hidden solar disk. Spectroscopic observations had revealed temperatures reaching into the millions of degrees. That created a physical question. What should such a hot outer atmosphere do? In the 1950s, a young physicist named Eugene Parker began examining the problem. Parker considered the behavior of the corona using fluid dynamics and thermodynamics. If the corona remained extremely hot, its material could not simply sit quietly around the sun in a perfectly static atmosphere. Under appropriate conditions, it should expand, and as Parker worked through the mathematics, the expansion produced a surprising result. The solar atmosphere should accelerate outward continuously, eventually reaching supersonic speeds. The sun, in other words, should generate a wind, not a breeze in the terrestrial sense. This would be a continuous flow of charged particles, mostly protons and electrons, spreading outward through the solar system. The idea was not immediately welcomed. A static or more gently structured solar environment seemed intuitive to many researchers. Parker's solution required the flow to pass through a critical point and continue outward at high speed. His paper faced skepticism during the publication process, yet it appeared in 1958. The title was restrained Dynamics of the Interplanetary Gas and Magnetic Fields. Its implications were not, if Parker was correct. The space between the planets was not simply an empty stage on which worlds moved. The sun was filling that space with a moving plasma. Evidence soon arrived from spacecraft. Early probes detected streams of charged particles flowing outward from the sun. Measurements by Soviet lunar missions and later by NASA's Mariner 2 helped establish the solar wind as a real and persistent phenomenon. Parker's theoretical wind had become measurable. Near Earth, its speed commonly reaches hundreds of kilometers per second, although conditions vary. The wind is not perfectly uniform. The sun rotates. Its magnetic field changes. Active regions appear and disappear. Coronal holes can produce relatively fast streams, while explosive events such as coronal mass ejections can send enormous structures through interplanetary space. Because the solar wind is electrically charged, it carries the sun's magnetic influence outward. Rotation twists this magnetic field into a vast spiral pattern, often called the Parker spiral. The result is an environment connecting the planets to the activity of the sun. Earth does not sit passively inside it. Our planet has a magnetic field that deflects much of the solar wind, creating the magnetosphere. When solar disturbances reach Earth, they can alter near-Earth space, intensify auroras, disrupt radio communication, affect satellites, and under severe circumstances influence electrical systems on the ground. Mars, lacking a strong global magnetic field today, interacts with the solar wind differently. Over geological time, that interaction has contributed to atmospheric loss. Comets respond visibly as well. Their ion tails can trace changing conditions in the solar wind like streamers carried by an invisible current. Yet the most important consequence for our journey lies farther outward. A wind cannot expand forever without encountering something. The sun is not alone in a perfect vacuum. Between the stars exists the interstellar medium, an extraordinarily thin mixture of gas, plasma, dust, magnetic fields, and energetic particles. As the sun moves through its local galactic environment, its solar wind pushes outward against this surrounding material. The interaction creates the heliosphere. It is often described as a bubble around the sun, although its exact shape is more complicated than a simple sphere. For decades, diagrams frequently depicted something resembling a comet, with a rounded front and a long tail trailing behind the moving solar system. Modern observations and models have produced more nuanced possibilities. The heliosphere's shape depends on interactions between solar plasma, interstellar material, magnetic fields, charge exchange processes, and the changing solar cycle. Some models suggest a more compact and structured form than the traditional long-tailed picture. There are still questions about its global geometry, but its existence is clear. Our planets live inside a cavity created by the Sun, and this cavity has internal boundaries. As the solar wind travels outward, it expands and gradually loses its ability to dominate the surrounding environment. Eventually it reaches the termination shock. Here the solar wind slows from supersonic to subsonic speeds relative to the characteristic wave speeds in the plasma. Beyond this lies a region called the Helios Heath. The solar wind continues through it, slower and compressed, approaching the boundary where its outward influence meets the interstellar medium. The outer boundary is the heliopause. For most of Parker's career, no spacecraft had reached it. The heliosphere was understood through theory, remote observations, and measurements made much closer to the Sun. Then 2 spacecraft launched in 1977 began moving toward the outer planets. Voyager 1 and Voyager 2 were not originally built around a mission to discover the heliopause. Their great opportunity came from an unusual arrangement of the outer planets that allowed gravity assist to carry spacecraft from one giant world toward another. Voyager 1 encountered Jupiter and Saturn. Voyager 2 continued past Uranus and Neptune as well. After the planetary encounters ended, both spacecraft kept traveling outward. Years became decades, the Sun grew fainter, the planets fell behind, and the Voyagers entered a region no functioning spacecraft had explored before. Their instruments began detecting changes. The populations of charged particles shifted. Cosmic rays from beyond the heliosphere became increasingly important. The magnetic and plasma environment evolved in ways scientists could compare with competing expectations. The spacecraft were approaching the place where Parker's solar wind finally surrendered its dominance. Eugene Parker lived long enough to see Voyager cross that frontier. He also lived to see a NASA spacecraft named in his honor, Parker Solar Probe, travel in the opposite direction, repeatedly approaching the Sun to study the corona and the origins of the wind he had predicted decades earlier. The story had stretched from mathematical equations to measurements near both extremes of the heliosphere. But the Voyagers were about to reveal something philosophically stranger. Humanity could cross the boundary created by the solar wind without truly leaving the Sun behind. And when Voyager 1 finally entered the interstellar medium, the meaning of the word escape became more complicated than ever. By the time Voyager 1 approached the outer boundary of the heliosphere, it had already completed the mission for which it was originally famous. Jupiter was decades behind it. So was Saturn. The spacecraft had photographed worlds that had previously existed mainly as distant points of light. It had revealed details in Jupiter's turbulent atmosphere, observed active volcanoes on Io, examined Saturn's rings, and transformed several moons from vague astronomical objects into recognizable places. Then its cameras were largely finished with their work. Voyager 1 was heading somewhere increasingly dark. At such distances, there was little reason to continue photographing the emptiness ahead. Instead, the spacecraft's remaining scientific instruments listened to an environment humans had never sampled directly. The journey became less visual, and in some ways, more profound. The Sun still appeared brighter than the surrounding stars, but its warmth had become negligible. Solar energy was too weak to power the spacecraft effectively. So Voyager depended on radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity. Their output gradually declines. Every year, the mission team has had to manage a shrinking energy budget. Instruments have been turned off over time. Heaters have been reduced or disabled where possible. Engineers have repeatedly found ways to extend a mission operating far beyond its original planetary objectives. Yet the scientific question ahead remained deceptively simple. When would Voyager leave the heliosphere? The spacecraft had already crossed the termination shock in 2004. The solar wind around it had slowed. Voyager entered the Helios sheath, the turbulent outer region where solar plasma is compressed as it approaches the surrounding interstellar medium. But the heliopause itself was still ahead. Scientists expected several signatures when the spacecraft crossed it. Particles associated with the solar environment should decrease. Galactic cosmic rays arriving from outside should become more abundant. The plasma conditions should change. The magnetic field might also behave differently, although predictions about its orientation were not straightforward. Then, during 2012, Voyager 1 recorded a dramatic change in energetic particles. Particles associated with the heliosphere dropped sharply. Galactic cosmic rays increased. Something important had happened. But interpreting a boundary no spacecraft had ever crossed was not trivial. Voyager 1's dedicated plasma instrument had stopped functioning decades earlier, so scientists could not directly measure the local plasma in the most obvious way. Instead, they had to become more inventive. Solar eruptions occasionally send disturbances outward through the heliosphere. When such disturbances eventually reached Voyager's distant environment, they could cause the surrounding plasma to oscillate. Voyager's plasma wave instrument detected these oscillations. From their frequency, scientists could estimate the density of electrons around the spacecraft. The density was much higher than expected inside the heliosphere. It was consistent with the interstellar medium. The evidence converged. Voyager 1 had crossed the heliopause in August 2012 at roughly 121 astronomical units from the Sun. For the first time, a functioning human-made object was sampling interstellar space directly. 6 years later, Voyager 2 followed. Its crossing occurred at a somewhat different distance, around 119 AU, and it retained a working plasma instrument. That made its observations especially valuable. The two crossings revealed that the heliosphere is dynamic. Its boundary responds to changing solar conditions and interactions with the surrounding interstellar environment. Humanity had now measured the transition from the Sun's plasma domain to the material between the stars from two different trajectories. It would be easy to describe this as leaving the solar system. In ordinary language, that is often exactly what happens. But astronomy requires a little more care. Voyager crossed the heliopause. It did not cross the outermost gravitational reaches of the solar system. The distinction is enormous. The heliopause lies a little more than 100 times Earth's distance from the Sun. The Oort cloud, if current models are broadly correct, extends thousands or tens of thousands of AU outward, perhaps farther. Voyager may therefore spend centuries travelling before reaching even regions associated with its inner portions. Tens of thousands of years could pass before the spacecraft traverses the wider domain usually associated with distant Oort cloud objects. By then, Voyager will have been silent for an almost incomprehensible length of time. Its radio transmitter will not be speaking to Earth. Its power sources will long since have become insufficient for communication. Whatever remains of the spacecraft will simply coast. This is the first great lesson Voyager offers about interstellar travel. Motion is easy to continue once nothing is trying very hard to stop you. The difficult part is maintaining function. A spacecraft can coast for millions of years if its trajectory remains undisturbed enough. A civilization cannot merely coast. Voyager does not need food. It does not need oxygen. It does not care about loneliness. Its electronic systems can eventually fail without threatening living passengers, and it does not need to slow down when it passes another star. It has no destination in the human sense. Voyager 1 is moving relative to the Sun at roughly 17 kilometers per second. That is extraordinarily fast compared with everyday experience. At that speed, it could cross the distance between London and New York in only a few minutes. But interstellar distances reduce impressive velocities to almost nothing. The nearest star system, Alpha Centauri, is about 4.37 light-years away. Voyager 1 is not heading there. But if we use its speed merely as a scale for comparison, traversing a similar interstellar distance would require tens of thousands of years. That number changes the nature of the problem. A human civilization might build a machine capable of surviving decades, perhaps centuries, but tens of thousands of years is not simply a longer mission. It is a different category of undertaking. 10,000 years ago, agriculture was still spreading through human societies. Most modern nations did not exist. Every spoken language has changed. Religions, governments, technologies, and cultures have risen and disappeared. A spacecraft journey lasting several times that interval would not connect two moments in one civilization in the way an airline route connects two cities. It would connect different eras of human history. And Voyager has another lesson. Communication does not escape the tyranny of distance either. Radio signals travel at the speed of light. As Voyager moves farther away, commands from Earth take longer to reach it, and its responses take equally long to return. For an interstellar spacecraft, delays would eventually be measured in years. There is no technology that can make useful information travel faster than light according to established physics. A crew near another star could not hold a conversation with Earth. Every exchange would become correspondence across time. Questions might be answered years after they were asked. Emergencies would belong entirely to those experiencing them. Voyager therefore represents both a triumph and a warning. It proves that machines can leave the heliosphere. It demonstrates that spacecraft can operate for extraordinary periods. It shows that the interstellar medium is physically reachable, but it also reveals how misleading the word reachable can become. Crossing a boundary is not the same as crossing the gulf. The heliopause is only the shoreline. The true ocean begins beyond it. And once the speed of Voyager is compared with the distance to even the nearest star, the next question becomes unavoidable. How large is that ocean, really? The distance between stars is difficult to understand because almost nothing in ordinary life prepares us for it. Numbers alone do not help very much. 4 light-years sounds manageable. 4 is a small number. Even 40 trillion kilometers remains strangely abstract. Once a number becomes large enough, adding more zeros does not necessarily make it feel larger. A better way to approach interstellar distance is to begin with the region we already know. Light travels from the Moon to Earth in a little more than 1 second. From the Sun, it takes a little over 8 minutes. From Jupiter, depending on the positions of Earth and Jupiter in their orbits, light requires tens of minutes. From Neptune, the journey takes roughly 4 hours. Already, the solar system is large enough that communication cannot be instantaneous. A command sent to a spacecraft near Neptune must cross billions of kilometers before arriving. Yet Neptune is still close when measured against the stars. After Neptune comes the Kuiper Belt, then the distant populations beyond it, then perhaps thousands of astronomical units away, the inner reaches of the Oort cloud. At 1 light-year from the Sun, light itself has been travelling for an entire year. Alpha Centauri lies more than 4 times farther away. The system contains 3 known stars, Alpha Centauri A, Alpha Centauri B, and the smaller red dwarf Proxima Centauri. Proxima is currently the closest of the 3 to us, at about 424 light-years. It is also known to host planets. For the first time in human history, we know that a planetary system exists around the nearest star to the Sun. That fact can make the destination feel almost accessible. But consider the scale another way. Suppose the distance between the Sun and Earth were compressed until it measured only 1 meter. On that scale, Neptune would orbit about 30 meters away. Voyager 1 would be more than 100 meters from the Sun. The outer Oort cloud, depending on the boundary chosen, could extend for many tens of kilometers, and the nearest star would still be hundreds of kilometers away. The planets occupy a tiny neighborhood compared with the space-separating stellar systems. This emptiness is one of the defining features of our region of the galaxy. Stars appear crowded when we look at the night sky because our vision compresses depth onto the celestial sphere. 2 stars that seem almost adjacent from Earth may actually be separated by enormous distances. The Milky Way contains hundreds of billions of stars, but its volume is so vast that most stars remain profoundly isolated from one another. Our Sun is no exception. That isolation has consequences for travel. Voyager 1 moves outward at roughly 17 kilometers per second relative to the Sun. At that speed, a journey across the distance to Proxima Centauri would take more than 70,000 years if the spacecraft were actually travelling in that direction. Voyager 2 is somewhat slower. New Horizons, although launched at tremendous speed from Earth, also operates on a scale where stellar journeys would require many tens of thousands of years. Clearly, an interstellar spacecraft intended for humans would need to travel much faster. Suppose we could reach 1% of the speed of light. That is around 3,000 kilometers per second. No spacecraft carrying humans has approached anything remotely like this velocity. But even at 1% of light speed, ignoring acceleration and deceleration, crossing 4.24 light-years would require more than 4 centuries. a 10% of light speed. The travel time falls to a little over 40 years. Now the journey begins to fit within a human lifetime. But the energy requirements rise dramatically. Speed is not something a spacecraft receives for free. To accelerate mass, energy must be supplied. The faster the desired velocity and the heavier the vehicle, the greater the energy requirement. And a crude interstellar spacecraft would probably not be light. It would need shielding, life support equipment, energy systems, redundant machinery, food production or storage, medical resources, living space, perhaps equipment for establishing some form of settlement at the destination. Every kilogram added to the spacecraft increases the difficulty of accelerating it. Traditional rockets face another problem. They must carry propellant. More propellant allows greater changes in velocity, but propellant itself has mass. Carrying that mass requires still more propellant. This relationship is captured by the rocket equation, one of the fundamental constraints of spaceflight. For chemical rockets, the exhaust velocity is limited by the energy available from chemical reactions. That works remarkably well for reaching orbit and sending probes across the solar system. It becomes deeply inadequate for journeys requiring a substantial fraction of light speed. The challenge is not that chemical rockets suddenly stop working beyond Neptune. The challenge is scale. A propulsion system excellent for planetary exploration can be almost irrelevant for interstellar transportation. There is also the question of stopping. Popular discussions of interstellar travel often focus on reaching high velocity, but a spacecraft traveling at 10% of light speed that arrives near another star is not finished. Unless the mission is intended as a high-speed flyby, the vehicle must decelerate. That requires another enormous change in velocity. If the spacecraft carries the necessary propellant for slowing down, that propellant must itself be accelerated during departure. The mass problem compounds. Alternative concepts attempt to avoid this in different ways. A light sail might receive energy from a powerful laser located near its home system, reducing the need to carry fuel for initial acceleration. A magnetic sail might interact with charged particles or magnetic fields to help decelerate. Fusion propulsion could potentially provide far higher exhaust velocities than chemical rockets. Antimatter offers extraordinary energy density in principle. Each idea changes part of the equation. None makes distance disappear, and distance creates another problem that propulsion alone cannot solve. Time at 40 years. A journey might fit within one human lifetime, but the spacecraft would need to operate reliably for decades without conventional maintenance infrastructure. At 400 years, generations would be born and die during the journey. At 4,000 years, the mission becomes almost impossible to separate from the evolution of the society undertaking it. The travelers would not merely be passengers. They would become descendants of passengers. Their destination would be a place chosen by people they had never met. Even if the spacecraft remained physically functional, its purpose would have to survive across generations. This is where interstellar distance becomes more than a measurement. It becomes an environment. It separates not only locations but causes from consequences. A decision made at departure might shape lives centuries later. A mechanical flaw overlooked during construction could become a problem for people born long after the engineers responsible were gone. A message sent home might reach Earth after political systems, technologies, and cultures had changed. Distance stretches everything. Maintenance, communication, memory, responsibility. The nearest star is therefore not simply farther away than Neptune. It belongs to a fundamentally different scale of travel, and yet distance alone does not forbid the journey. If a spacecraft could move fast enough, centuries could become decades. That possibility seems to offer an escape from the problem, but increasing speed does not merely solve difficulties. Beyond a certain point, it begins creating new ones. And the faster we try to cross the interstellar ocean, the less empty that ocean becomes. The obvious answer to an enormous distance is greater speed. Human transportation has followed this logic repeatedly. Walking gave way to horses and sailing ships. Steam engines compressed journeys that once required weeks. Aircraft crossed oceans in hours. Rockets reached the moon in days. The distance did not change. Our velocity did. It is reasonable to assume that interstellar travel will follow the same pattern. Build faster spacecraft and the stars become closer in practical terms. Physics does allow enormous velocities. There is no known principle preventing a spacecraft from traveling at 1% of the speed of light, or 10%, or even much faster, provided it remains below the speed of light. But the word provided hides nearly the entire problem. A spacecraft does not simply possess speed, it must acquire it. To understand why this becomes difficult, consider the spacecraft that carried humans to the moon. The Saturn V was one of the most powerful machines ever constructed. At launch, most of its mass consisted of propellant. This was not inefficient engineering. It was a consequence of rocket propulsion. A rocket moves forward by throwing mass backward. To produce a large change in velocity, it must expel propellant at high speed, but the propellant required later in the journey must be carried during the earlier part. That propellant has mass. Accelerating it requires additional propellant. The relationship becomes increasingly unforgiving as the desired change in velocity grows. Chemical rockets are constrained by the amount of energy chemical reactions can release per unit mass. Their exhaust velocities are excellent for moving through the solar system. They are nowhere near what would be desirable for rapid interstellar travel. One alternative is electric propulsion. Ion engines and related systems accelerate charged particles using electric fields. Their thrust can be extremely small, but their exhaust velocities can greatly exceed those of chemical rockets. Given enough time, a spacecraft can gradually build substantial velocity. Electric propulsion has already been used successfully on real missions, but there is a trade-off. High efficiency does not automatically mean high power. An ion engine may operate for months or years, slowly changing a spacecraft's velocity. For many planetary missions, this is extremely useful. For a massive crewed vehicle attempting to reach a meaningful fraction of light speed, the required power becomes another formidable problem. Where would that energy come from? Near Earth, solar panels work well. Far from the sun, sunlight weakens according to the inverse square law. Double the distance from the sun and the available solar energy per unit area falls to 1/4. At interstellar distances, relying on ordinary sunlight from our sun becomes impractical. The spacecraft must carry or receive another source of energy. Nuclear fission is one possibility. Fission reactors can produce large amounts of energy for long periods without depending on sunlight. Nuclear thermal propulsion could also heat propellant to temperatures higher than conventional chemical combustion allows, improving performance. But fission still does not provide the enormous exhaust velocities ideal for fast interstellar journeys. Fusion is more enticing. Stars themselves are powered by nuclear fusion. In fusion reactions, light atomic nuclei combine and release energy. Certain proposed fusion propulsion systems could, in principle, achieve performance far beyond chemical or fission rockets. One of the most famous historical studies was Project Daedalus, developed in the 1970s by the British Interplanetary Society. Daedalus was not intended to carry humans. It was a conceptual robotic interstellar probe. Its designers considered a two-stage fusion spacecraft that might reach a significant fraction of light speed and travel to another star within a human lifetime. The study was valuable precisely because it tried to treat interstellar travel as an engineering problem rather than a fantasy, and the result was enormous. The proposed spacecraft required vast quantities of fusion fuel and technologies that did not exist. Decades later, controlled fusion remains an active field of research, but humanity has not built a practical fusion rocket. Then there is antimatter. When matter and antimatter meet, their mass can be converted into other forms of energy with extraordinary efficiency. In principle, this makes antimatter one of the most energy-dense possibilities known to physics. In practice, producing antimatter is extraordinarily inefficient with present technology. Only tiny quantities have been created. Storing significant amounts is also extremely difficult because antimatter cannot simply touch ordinary matter. A propulsion system requiring large stores of antimatter therefore remains far beyond present engineering. Another strategy removes much of the energy source from the spacecraft. Instead of carrying fuel, the vehicle could be pushed by light. Photons have no rest mass, but they carry momentum. When light reflects from a sail, it can exert a small pressure. Sunlight can push solar sails, and several spacecraft have demonstrated versions of this principle. For interstellar travel, a far more powerful possibility is beamed propulsion. A huge laser array could direct energy toward a very light sail, accelerating a small spacecraft to extreme velocity without requiring the probe to carry its own main propulsion energy. Breakthrough Starshot has explored the concept of sending gram-scale probes toward Alpha Centauri at perhaps around 20% of light speed using powerful ground-based lasers. The concept remains highly ambitious and faces major technical challenges, but it reveals an important principle. Interstellar velocities become more plausible when the spacecraft becomes extremely small, and that creates a problem for humans. A tiny probe might weigh grams. A human interstellar spacecraft could weigh thousands, millions, or perhaps far more kilograms depending on its design. The difference matters enormously. Energy requirements scale with mass. A laser capable of accelerating a wafer-scale probe is not automatically capable of accelerating a habitat containing people. At sufficiently high velocities, relativity must also be considered. As an object approaches the speed of light, the energy required to increase its speed rises dramatically. No object with rest mass can be accelerated to the speed of light according to special relativity. But for journeys to nearby stars, we do not need to approach that limit closely before another difficulty appears. The environment ahead becomes dangerous. At ordinary spacecraft speeds, a microscopic dust grain is usually an inconvenience that shielding can manage. At a substantial fraction of light speed, the same grain carries enormous kinetic energy relative to the spacecraft. Individual atoms of interstellar gas also strike the vehicle with energies that can produce radiation and damage materials. The faster the spacecraft travels, the more severe these interactions become. Speed shortens the journey, but speed also increases the energy that must be generated, controlled, and eventually removed. It increases the consequences of impacts. It complicates shielding, and unless the destination is merely something to flash past, the spacecraft must eventually slow down. The problem, therefore, has an uncomfortable symmetry. Acceleration is only half the journey. Every extraordinary velocity gained near the Sun becomes extraordinary velocity that must somehow be lost near another star. A faster spacecraft may solve the problem of time while creating problems of energy, heat, shielding, mass, and deceleration. This is why speed alone is not the answer. The real question is, what kind of engine could accelerate a useful spacecraft to interstellar velocity without requiring impossible quantities of fuel or energy? And when we examine the engines that might do it, we find ourselves standing at a peculiar boundary. Some already exist, some are being tested, some are permitted by known physics but remain far beyond our engineering, and some may never become practical at all. There is a large difference between a machine that violates no known law of physics and a machine that can actually be built. Interstellar travel lives inside that difference. The history of spaceflight encourages optimism. Rockets once belonged to speculation. Artificial satellites became real. Humans walked on the moon. Robotic spacecraft reached every major planet, landed on comets and asteroids, and entered interstellar space. But these achievements were not produced by discovering ways around physics. They came from learning how to work within it. Any serious interstellar engine must do the same. The most mature option remains chemical propulsion. Chemical rockets are powerful. They can produce enormous thrust, lift vehicles from planetary surfaces, and accelerate spacecraft onto trajectories through the solar system. Their limitation is not reliability. It is energy density. Chemical bonds contain only a modest amount of energy compared with nuclear reactions. Once the desired velocity rises into the thousands of kilometers per second, carrying enough chemical propellant becomes impractical. Nuclear fission offers a step upward. In a nuclear thermal rocket, a reactor heats a propellant, often envisioned as hydrogen, which then expands through a nozzle. Such systems could potentially provide better efficiency than conventional chemical engines. The underlying physics is well understood, and experimental nuclear thermal rocket programs were pursued during the 20th century. Modern research has continued exploring the concept. For fast journeys within the solar system, nuclear thermal propulsion could become extremely valuable. For rapid journeys to another star, it remains insufficient. Electric propulsion takes a different approach. Rather than heating large quantities of propellant and ejecting them quickly, electric thrusters accelerate much smaller amounts of material to far higher exhaust velocities. Ion propulsion has already demonstrated remarkable endurance. NASA's Dawn spacecraft, for example, used ion engines to explore Vesta and Ceres. Its acceleration at any moment was gentle, but the engine could operate for long periods. That cumulative effect allowed changes in velocity that would have required much more propellant from conventional systems. Still, the power requirement remains: to accelerate a large interstellar vehicle rapidly using electric propulsion. An extraordinary energy source would be needed. This brings us to fusion. Fusion occupies an unusual position in discussions of interstellar flight because the reaction itself is not hypothetical. Fusion occurs naturally inside stars. Humans have produced fusion reactions experimentally. Researchers are actively working toward controlled fusion systems capable of delivering useful energy. What humanity does not possess is a practical fusion propulsion system capable of accelerating a spacecraft toward another star. Several designs have nevertheless explored the possibility. Project Daedalus proposed using small pellets of fusion fuel ignited repeatedly, creating a sequence of energetic pulses that would accelerate an uncrewed probe. Later concepts have reconsidered fusion propulsion using different fuels, ignition methods, magnetic confinement strategies, and spacecraft architectures. The attraction is clear. Fusion could provide exhaust velocities vastly greater than chemical rockets while using fuels with far higher specific energy. But every part of that sentence contains engineering difficulty. Fusion fuel must be stored. Reactions must be initiated and controlled. The released energy must be directed usefully. Waste heat must be removed. The engine must survive continuous operation. And all of this must occur aboard a spacecraft expected to function far from repair facilities. Then there is antimatter. On paper, antimatter seems almost irresistible. When matter and antimatter annihilate, a large fraction of their mass can be converted into energy. Compared with chemical reactions, the available energy per unit mass is enormous, but antimatter illustrates perfectly why theoretical possibility and practical technology must be separated. We can produce antimatter. Particle accelerators routinely create antiparticles. We can trap small numbers of them using electromagnetic fields, but the quantities involved are tiny. Producing antimatter requires enormous amounts of energy, and current processes are extraordinarily inefficient. Storing macroscopic quantities would introduce another challenge. Antimatter cannot be allowed to contact the walls of an ordinary container. Containment would need to remain exceptionally reliable throughout launch, acceleration, and a potentially decades-long voyage. For now, antimatter propulsion belongs to the category of physically motivated but technologically remote possibilities. Light sails offer almost the opposite philosophy. Instead of carrying an energetic fuel, remove the engine. Let something else provide the push. A sail can receive momentum from photons. Sunlight can do this gently, and solar sailing has already been demonstrated. For interstellar missions, sunlight becomes too weak at great distances, so proposals often replace it with a powerful artificial beam. A laser array near Earth or elsewhere in the inner solar system could focus light onto a reflective sail. The spacecraft would carry little or no propellant for acceleration. This dramatically changes the mass equation. It is especially attractive for tiny robotic probes. A gram-scale vehicle attached to an ultralight sail might, under highly ambitious proposed systems, be accelerated to a significant fraction of light speed. If such probes could be built, aimed accurately, protected during flight, and equipped to return useful data, they could potentially reach the Alpha Centauri system within decades rather than millennia. But scaling the concept to humans is difficult. A crewed spacecraft requires mass. Even an extremely minimalist habitat needs structure, shielding, power, life support, equipment, and people. Accelerating thousands of tons with light would require an energy and beam infrastructure vastly beyond that needed for a tiny probe. The sail itself would face severe material demands. The beam would need to remain accurately directed, and once the spacecraft approached its destination, it would still need a method of slowing down. Some proposed solutions use the destination star's light, magnetic fields, or other forms of sailing for deceleration. Whether such systems could operate reliably at the required scale remains uncertain. Other concepts are even more exotic but still connected to established physics. Magnetic sails could interact with charged particles. Electric sails could exploit plasma environments. Nuclear pulse propulsion could accelerate spacecraft through repeated nuclear explosions behind a massive pusher system. Each has advantages. Each also carries severe engineering, environmental, political, or operational challenges. What is striking is not the absence of ideas. It is the absence of a complete system. We know many ways to produce thrust. We know many ways to release energy. We know materials that can survive remarkable conditions. But an interstellar spacecraft needs all of these capabilities to work together at unprecedented scales for unprecedented periods. The engine must be powerful but not impossibly massive. The fuel must be energetic but safely manageable. The vehicle must accelerate without destroying itself. The propulsion system must operate reliably for years or decades. Heat must escape. Shielding must survive. Navigation must remain accurate. And some method must exist for slowing at the destination. No current propulsion technology satisfies all of these requirements for human interstellar travel. That statement is not the same as saying none ever will. Fusion research may advance. Beamed propulsion may become practical for robotic missions. New materials could change engineering limits. Energy production may improve dramatically. But none of these possibilities allows us to skip the next problem. Suppose an engine existed tomorrow that could push a spacecraft to 10 or 20% of light speed. The journey would become shorter, but the space ahead would become more dangerous. At those velocities, darkness is not empty. A grain smaller than a seed can become a projectile carrying destructive energy. Individual atoms can become a radiation hazard, and the spacecraft would have to endure this invisible bombardment not for seconds, but for years. The engine may therefore be only the beginning. The faster we learn to travel, the more carefully we must ask what is waiting in our path. At the speeds of ordinary spaceflight, the space between worlds seems almost perfectly empty. This impression is useful, but incomplete. Interplanetary and interstellar space contain matter. The density is extremely low compared with Earth's atmosphere. Yet there are atoms, ions, electrons, dust grains, cosmic rays, magnetic fields, and occasional larger particles scattered through the darkness. For Voyager, this thin environment is something to measure. For a spacecraft travelling at a substantial fraction of the speed of light, it becomes something to survive. The difference comes from kinetic energy. A small particle moving slowly relative to a spacecraft carries little energy. Increase the relative velocity, and the consequences of a collision grow rapidly. At 10% of light speed, a spacecraft would move at roughly 30,000 kilometers per second. A journey to the nearest stars could then be measured in decades. But every particle ahead would strike the spacecraft at approximately that relative velocity. Even a tiny grain of dust could release substantial energy on impact. Larger grains, though much rarer, could be far more serious. This does not automatically make high-speed interstellar flight impossible. Spacecraft already use shielding against impacts. The International Space Station, for example, incorporates protective structures designed to reduce damage from small pieces of orbital debris and micrometeoroids. Interstellar shielding, however, would operate under radically different conditions. One possible strategy is a thick sacrificial shield at the front of the vehicle. Material could absorb repeated impacts and gradually erode. Another possibility involves multiple separated layers, allowing an incoming particle to break apart before its fragments reach deeper structures. Some concepts consider clouds of material released ahead of the spacecraft, while others explore electromagnetic methods for interacting with charged particles. No single solution has yet been demonstrated for a crewed spacecraft moving at relativistic fractions of light speed, and dust is only part of the problem. The interstellar medium contains gas. Much of it consists of hydrogen. At ordinary velocities, encountering individual hydrogen atoms seems almost meaningless. At sufficiently high relative speeds, those particles can interact with spacecraft materials in energetic ways. The spacecraft effectively transforms the thin interstellar gas into a stream of high-energy particles. Radiation becomes inseparable from velocity. Then there are galactic cosmic rays. These energetic particles originate from sources beyond the solar system, including violent astrophysical processes within the galaxy and beyond. Earth's atmosphere and magnetic field protect life at the surface from much of this radiation. Astronauts outside Earth's protective environment receive higher doses. A crew traveling between stars would spend years beyond Earth's magnetosphere, and eventually beyond much of the heliosphere's modulation of lower energy cosmic radiation. Shielding can reduce exposure, but radiation protection adds mass. Mass then makes acceleration more difficult. The solution to one problem strengthens another. This pattern appears repeatedly in interstellar engineering. Add shielding and the spacecraft becomes heavier. Reduce shielding and the crew faces greater risk. Increase speed to shorten radiation exposure, and collisions with interstellar material become more energetic. Travel more slowly to reduce impact energies, and the crew must remain in space longer. There may be an optimal balance, but there is no obvious free solution. Heat creates another constraint. Every spacecraft generates waste heat. Computers produce it. Life support systems produce it. Power systems produce it. Humans themselves produce it. On Earth, heat can be transferred into surrounding air or water. In space, there is no surrounding atmosphere to carry it away. A spacecraft ultimately has to radiate excess heat into space as electromagnetic radiation. This requires radiators. For an interstellar vehicle with a powerful reactor or propulsion system, those radiators could become large structures. They must survive acceleration and impacts. They must operate reliably for decades, and their temperature determines how efficiently they can radiate energy. Waste heat is one reason enormous power production does not automatically solve every engineering problem. Energy must not only be generated, it must also be controlled and discarded after it's done useful work. Navigation at extreme velocity is equally unforgiving. A tiny angular error at departure can become an enormous positional error after travelling several light years. Stars themselves move. Planets orbit their stars. A destination is not a fixed point painted onto the sky. An interstellar mission must predict where its target will be when the spacecraft arrives. That is possible in principle. Astronomy already measures stellar positions and motions with extraordinary precision, but a spacecraft travelling for decades may need to make corrections along the way. At high speed, even small changes in trajectory can require substantial energy. Then comes the question often hidden behind the excitement of acceleration. How does the spacecraft stop? Suppose a vehicle reaches 20% of light speed. At that velocity, Alpha Centauri becomes reachable on a timescale of a few decades, ignoring the periods of acceleration and deceleration. But if the spacecraft carries no method of slowing down, the encounter with the star system could be astonishingly brief. A probe might collect data during a rapid passage. A human crew cannot establish a settlement while crossing a planetary system at tens of thousands of kilometers per second. The kinetic energy that made the journey short must somehow be removed. A conventional rocket could turn around and fire its engine in the opposite direction, but that requires fuel, and that fuel had to be accelerated during departure. Beamed propulsion might solve part of the acceleration problem by leaving the energy source at home, but the destination may not possess an equivalent laser array waiting to slow the spacecraft. Proposed magnetic sails might use the interstellar medium or the stellar wind near the destination to decelerate gradually. Photonic sails might interact with light from the destination star. Other concepts combine multiple systems. All remain areas of theoretical and engineering investigation rather than demonstrated human transport technology. And there is a deeper issue. A high-speed spacecraft contains enormous kinetic energy simply because it is moving. That energy does not care whether the vehicle is functioning correctly. A navigation failure, shielding failure, or collision at extreme speed can have consequences far beyond those experienced by slower spacecraft. Reliability, therefore, becomes central. A machine travelling between stars cannot depend on frequent replacement parts from Earth. It must diagnose problems, repair itself or allow its crew to repair it, preserve manufacturing capability, maintain software and hardware over timescales longer than most technologies on Earth remain in service. Our civilization routinely replaces complex machines after years or decades. An interstellar vessel may need essential systems to remain maintainable across generations. The challenge is no longer merely building something strong enough to survive launch. It is building something capable of remaining a functioning world while moving through a hostile environment for a significant fraction of a human lifetime, or much longer. And this is where the engineering problem quietly becomes biological. A robotic probe can be designed around radiation tolerance, redundancy, and machine repair. Humans bring requirements that cannot simply be switched off. Bones respond to gravity. Cells respond to radiation. Minds respond to isolation. Bodies age. Food must be produced. Air must be renewed, water must circulate, waste must return to useful forms. If speed cannot eliminate these requirements, then an interstellar spacecraft must carry a small piece of Earth with it, and maintaining that piece of Earth may prove harder than building the engine that carries it. A spacecraft can tolerate conditions that a human body cannot. Metal does not need oxygen. Electronics do not suffer loneliness. A robotic probe can spend decades in darkness without exercise, sleep, food, companionship, or any understanding of where it is going. Human beings are different. We evolved on the surface of a particular planet, under conditions so familiar that they're easy to overlook. Earth provides gravity continuously. Its atmosphere maintains pressure around us. Its magnetic field and atmosphere reduce our exposure to harmful space radiation. Its biosphere produces food, cycles water, processes waste, regulates gases, and supports an immense web of organisms that ultimately makes human civilization possible. We carry none of these things automatically when we leave. Spaceflight therefore begins with an unusual engineering requirement. The vehicle must recreate enough of Earth to keep its passengers alive. For a journey lasting days, this can be achieved largely by carrying supplies. For months, recycling becomes increasingly important. For years, reliability and biological health become central concerns. For decades or centuries, the spacecraft begins to resemble an ecosystem. We already have one extraordinary laboratory for understanding part of this problem. The International Space Station has been continuously inhabited since 2000. Its crews have demonstrated that humans can live and work in space for many months. Water is recycled. Carbon dioxide is removed from cabin air. Oxygen can be generated. Exercise systems help reduce some of the physical effects of microgravity. Medical data from astronauts have given researchers a growing understanding of how the human body responds to prolonged spaceflight. But the station also reveals how dependent human spaceflight remains on Earth. Cargo vehicles deliver food, equipment, experiments, spare parts, and other supplies. Crews rotate. Mission control provides continuous support. If a critical system fails, engineers on the ground can work with astronauts to develop solutions. An interstellar spacecraft would lose much of this safety net. The first biological problem would be gravity. Humans evolved under approximately 1 Earth gravity. Remove that constant loading and the body adapts. Muscles weaken, bones lose mineral density, fluids shift toward the upper body. The cardiovascular system changes. Balance and spatial orientation are affected. Astronauts can counter some of these effects through regular exercise. But exercise does not perfectly reproduce the biological environment of Earth's gravity. For a mission lasting decades, the long-term consequences of living in microgravity would be a serious concern. Artificial gravity could provide a solution. Instead of generating gravity in the science fiction sense, a spacecraft could rotate inside a sufficiently large rotating habitat. Occupants would experience an apparent force toward the outer wall. That wall could serve as the floor. The basic physics is straightforward. The engineering is less so. A rotating habitat must be large enough and rotate at an appropriate rate to avoid uncomfortable effects. Its structure must withstand continuous stresses. Bearings, joints, seals, and other systems must remain reliable. If the entire spacecraft rotates, docking and propulsion become more complicated. If only part rotates. The interface between rotating and non-rotating sections introduces its own challenges. Still, among the major problems of interstellar travel, artificial gravity is at least conceptually understandable. Radiation is more difficult. Outside Earth's protective environment, crews are exposed to energetic particles from the Sun and the wider galaxy. A sufficiently thick layer of matter can provide shielding. Water can help. So can certain plastics and other hydrogen-rich materials. A large habitat might place water tanks, food stores, or other useful mass around occupied areas so that the same material serves multiple purposes. But once again, protection means mass. A habitat surrounded by thick shielding is safer but harder to accelerate. The spacecraft designer must continually trade one necessity against another. Then comes air. A small leak on Earth is inconvenient. A leak in an interstellar spacecraft can become an existential problem. The atmosphere must remain within safe pressure and composition ranges. Carbon dioxide must be removed. Oxygen must be replenished. Trace contaminants must be controlled. Humidity must be managed. and these systems must continue operating for extraordinary periods. Water presents a similar challenge. Humans require it for drinking, hygiene, food production, and industrial processes. Carrying enough water for centuries without recycling would be unrealistic for most proposed designs. So water must circulate. Urine, humidity, wastewater, and other sources must be processed and returned to usable forms. Current spacecraft already recycle water to impressive degrees. An interstellar vessel would need to push recycling much closer to a closed loop. But perfectly closed systems are extraordinarily difficult. Materials are lost, chemicals accumulate where they are not wanted, filters degrade, microorganisms evolve, components corrode. A system can work for years and still fail on a timescale of centuries. Food makes the problem even deeper. Stored food has finite longevity. A multi-generational mission would almost certainly require biological production. Plants could provide calories while also participating in oxygen production and carbon dioxide removal. Algae or microorganisms might play additional roles. Waste products could become nutrients. In principle, the spacecraft could contain a carefully designed ecological cycle. But Earth's ecosystems are complex because stability emerges from countless interacting organisms and chemical processes. Simplifying that complexity into a small artificial biosphere is difficult. Experiments with closed ecological systems on Earth have shown how unexpected imbalances can emerge. Oxygen concentrations can change. Species can thrive or collapse. Nutrients can become trapped in unexpected places. Microbial populations can behave differently from predictions. A generation ship cannot simply open a window when its ecosystem drifts out of balance. Medicine would also change. A spacecraft carrying hundreds or thousands of people would experience ordinary illness and injury. There would be dental problems, infections, pregnancies, genetic disorders, accidents, aging, potentially cancers influenced by radiation exposure. The ship would need medical expertise and equipment, but over centuries, expertise cannot reside in one group of specialists. Knowledge must be preserved and transmitted. Medicines must be manufactured or replaced. Medical devices must be repaired. The vessel would need some ability to reproduce the technological infrastructure that keeps its inhabitants alive. And reproduction raises questions we've barely begun to investigate. No human being has ever been conceived, developed through pregnancy, born, and grown to adulthood in reduced gravity or microgravity. We do not know whether healthy human development across generations is possible under such conditions. Artificial gravity might reduce this uncertainty, but it has not been tested across human generations. An interstellar ship would therefore be carrying not only passengers, but an experiment extending across the entire human life cycle. Then there is psychology. Space is not merely physically empty, it is socially isolating. Crews on existing missions know they will return to Earth. They can communicate regularly with families. They can look through a window and see the planet below. Interstellar travelers would experience something fundamentally different. Earth would become a bright point. Then an ordinary star. Messages would take months and eventually years. For later generations, Earth might be a place known only through recordings, history, and inherited stories. The mission would cease to feel like a voyage away from home. The ship itself would become home. At that point, a profound transformation occurs. The central engineering question is no longer how to keep passengers alive until arrival. It is how to maintain a functioning human society inside a machine. Children would be born there. They would inherit responsibilities they never chose. They would maintain systems designed by ancestors. They would live within an environment whose failure could threaten everyone they knew. And if the journey lasted long enough, the people arriving at another star might have no personal memory of the world that launched them. A spacecraft designed for such a journey would not really be a spacecraft in the familiar sense. It would be a settlement with an engine, a habitat with a trajectory, a civilization enclosed within walls. And once we recognize that, another question becomes unavoidable. Even if we could build such a world, could a human society remain stable inside it for centuries? A generation ship begins with an uncomfortable fact. Some of the people who depart would never see the destination. They might spend their entire lives traveling between stars. Their children might do the same. Perhaps their grandchildren as well. If the voyage lasted several centuries, The people who eventually arrived would be descendants of the original crew, born inside a vessel they did not design and committed to a mission they did not choose. This changes the meaning of exploration. A conventional expedition is temporary. Explorers leave home, travel through unfamiliar territory, and usually intend either to return or to establish themselves somewhere they can reach within their own lifetimes. A generation ship would ask human beings to maintain a purpose across lives separated by centuries. The spacecraft would therefore need more than engineering. It would need continuity. At first, the problem appears numerical. How many people would be required? A very small population is easier to support because it needs less living space, food, water, and energy. But small populations create biological risks. Over generations, limited genetic diversity can increase the probability of harmful inherited conditions and inbreeding. A larger population offers more genetic variation, but it also demands a much larger spacecraft. Researchers have used population models to explore possible minimum crew sizes under different assumptions. The results vary widely because they depend on reproductive planning, genetic diversity, voyage duration, mortality, accidents, medical capabilities, and whether stored genetic material is available. There is no universally accepted number, and the uncertainty itself is revealing. No human population has ever lived for centuries inside a closed spacecraft. Biology is only the first layer. The ship would also need an economy. Not necessarily money in the familiar sense, but systems for allocating scarce resources. Energy would be finite. Living space would be finite. Raw materials would be finite unless the vessel could obtain resources during its journey, which would be difficult in the emptiness between stars. Manufacturing capacity would therefore matter enormously. A modern technological society depends on a planetary network of mines, factories, laboratories, farms, transport systems, and specialized workers. No spacecraft could carry that entire industrial civilization in its current form. Yet a generation ship would need to repair itself. A pump designed on Earth might fail 200 years later. A circuit board might become unusable. A pressure valve might crack. A sensor might degrade. The original manufacturer would be light years away. Replacement parts would need to be stored or made aboard the vessel. This suggests a requirement deeper than redundancy. The ship might need an industrial ecology. Metals would have to be recovered and reshaped. Polymers might need to be recycled. Electronic components might need to be fabricated. Tools would need tools capable of repairing them. Eventually, the vessel must preserve not only machines but the ability to make machines. Knowledge becomes a physical resource. A digital archive could contain enormous amounts of information, but an archive is useful only if people can access and understand it. Languages evolve. Educational priorities change. Technical knowledge can disappear when it is no longer practiced. On Earth, civilizations have repeatedly lost skills once maintained by earlier generations. An interstellar society could not assume that storing instructions guarantees competence centuries later. Engineers would need to train engineers. Doctors would need successors. Ecologists would need to teach the management of the ship's biological cycles. Navigation, power generation, computing, agriculture, materials science, and medicine would have to remain living traditions. Education would become part of the life support system. So would social stability. Human communities contain disagreement. Political systems change. Values evolve. People compete for status, resources, and influence. A generation ship would not remove these features of human behavior. It would confine them. This raises questions for which physics provides no equations. What political system could survive for centuries inside a closed habitat? How would authority be transferred? Could people leave one community and join another? What happens when a minority rejects a decision but has nowhere else to go? How should resources be distributed during shortages? What happens if later generations decide that reaching the original destination is no longer worth the risks? The people who launched the ship could write laws. They could preserve a constitution. They could design institutions. But they could not govern the distant future directly. A society born aboard the vessel would eventually develop its own culture. Perhaps its inhabitants would still think of themselves as travellers. Perhaps they would not. For someone born halfway through a 400-year journey, the destination would be almost as abstract as Earth. The ship would be the only landscape personally known. Its corridors would be childhood places. Its rotating habitats would be home. The artificial cycle of illumination would define morning and evening. The machinery behind the walls would be as ordinary as weather is to us. Earth might survive culturally as an origin story. Its oceans, forests, storms, insects, deserts, and open horizons could become things encountered mainly through recordings. This creates a psychological challenge unlike isolation on present-day spacecraft. Current astronauts remain members of an Earth-based civilization. Generation ship inhabitants would gradually become members of a ship-based civilization, and that transformation might be necessary. A community cannot spend centuries thinking of itself as temporarily trapped in transit. It would need meaningful lives during the journey rather than lives postponed until arrival. People would need art, friendship, privacy, celebration, work, education, play, love, places where nothing important was happening. A ship designed only for survival might prove unsuitable for human beings, even if its oxygen levels remained perfect. The architecture would therefore need to support culture as deliberately as it supported biology. There is also the possibility of conflict between survival and freedom. A closed population may require careful management of births to prevent overcrowding. Resources may impose limits on consumption. Certain activities could endanger everyone. A careless fire, biological contamination, or damage to a critical habitat might have consequences for the entire population. How much individual freedom could exist inside a world where environmental mistakes are shared? There is no experimental answer. Humanity has built submarines, polar stations, orbital habitats, and isolated communities. None reproduces the combination of duration, isolation, dependence, and irreversibility of an interstellar generation ship. This is why such vessels remain thought experiments as much as engineering proposals. They reveal something important about the original question. Perhaps the difficulty of escaping the solar system is not simply that our rockets are too slow. Perhaps the greater challenge is that interstellar distances demand a form of civilization we have never created, one capable of maintaining technology without planetary industry, one capable of sustaining ecosystems without a natural biosphere, one capable of preserving knowledge without external institutions, and one capable of giving generation after generation a meaningful existence inside an artificial world. Yet we are not completely without evidence. Small pieces of the larger problem are already being tested. Spacecraft are operating for decades. Closed-loop life support systems are improving. Astronomers are discovering nearby planets. Engineers are experimenting with new propulsion methods. And robotic explorers are slowly mapping the environment through which any future interstellar vessel would have to travel. The road to another star, if it ever exists, may therefore be assembled from technologies and observations already beginning around us. The question is whether those pieces are converging toward a path, or merely showing us how difficult the path really is. The first machines to approach the problem of interstellar travel were not built to reach another star. They were built to explore our own neighborhood. That distinction matters because almost everything we know about operating far from Earth has been learned gradually, through spacecraft designed for more immediate destinations. Each mission solves a smaller problem. Together, they reveal the scale of the larger one. Voyager remains the clearest example. When Voyager 1 and Voyager 2 launched in 1977, their primary objectives lay among the giant planets. No engineer expected their active missions to become experiments lasting nearly half a century. Yet their survival has taught us something fundamental. Complex machines can remain functional in deep space for decades. They can endure radiation, extreme cold, enormous communication delays, and the gradual decline of their power sources. But Voyager has also revealed the cost of longevity. Its systems are aging. Electrical power from its radioisotope generators steadily decreases as the plutonium fuel decays and thermocouples degrade. Engineers must decide which instruments can remain active. Systems once considered necessary have been shut down to preserve others. Every additional period of operation is achieved by careful management of a spacecraft that cannot be physically repaired. That experience is valuable because an interstellar probe would face the same problem on a much longer timescale. New Horizons provides another lesson. Launched in 2006, it crossed the solar system to Pluto in less than a decade, using a powerful launch and a gravity assist from Jupiter. In 2015, it transformed Pluto from a blurred, distant object into a world with mountains, plains, glaciers, haze layers, and extraordinary geological complexity. Later, it encountered Arrokoth, a small Kuiper Belt object more than 6 billion kilometers from the Sun. The mission demonstrated how precisely a spacecraft can be navigated across immense distances toward a tiny target, but New Horizons is still operating within the Sun's extended neighborhood. Its journey also shows how difficult exploration becomes when light and power fade. Solar panels that work efficiently near Earth would be far less useful at Pluto. Like Voyager, New Horizons relies on a radioisotope power source. Energy is one of the recurring currencies of deep space. Closer to the Sun, another spacecraft has been exploring the opposite extreme. Parker Solar Probe repeatedly dives through the Sun's outer atmosphere, traveling faster relative to the Sun than any previous human-made object. Its velocity during close solar encounters reaches hundreds of thousands of kilometers per hour. This is an extraordinary engineering achievement, but Parker's speed comes largely from falling deep into the Sun's gravitational field, assisted by repeated encounters with Venus that reshape its orbit. It is not an interstellar propulsion system. Still, the mission matters because it is studying the solar wind close to its origin. Voyager samples that wind where it finally yields to interstellar space. Parker studies it where it is born. Together, these missions connect two ends of the heliosphere. Other spacecraft contribute different pieces. Solar sails have demonstrated that light itself can provide propulsion. Japan's Ikaros mission successfully used a solar sail in interplanetary space. The Planetary Society's Light Sail 2 demonstrated controlled solar sailing in Earth orbit. These vehicles were not attempts to reach another star, but they confirmed an important principle. A spacecraft can exchange momentum with photons without consuming conventional propellant. For interstellar concepts based on powerful laser beams, that principle is essential. Laboratories on Earth are working on another piece of the puzzle. Laser technology continues to improve. Materials can be manufactured in increasingly thin and reflective forms. Researchers study how intense beams interact with potential sail materials and how tiny spacecraft might navigate, communicate, and survive extreme acceleration. None of this means a laser-driven interstellar probe is ready. The gap between a laboratory component and a complete mission remains enormous, but the relevant questions are becoming experimental rather than purely philosophical. Astronomy is also changing the destination. For centuries, the stars were simply stars. Now we know that planets are common. Thousands of exoplanets have been confirmed, and statistical studies indicate that planetary systems are widespread throughout the galaxy. Some orbit nearby stars. Proxima Centauri hosts at least one confirmed planet, Proxima Centauri b, with a minimum mass broadly comparable to Earth's. Whether it is habitable is another question. Proxima is an active red dwarf capable of powerful flares. The planet's atmosphere, surface conditions, magnetic environment, and long-term history remain uncertain. A planet located at a distance where liquid water could theoretically exist is not automatically an Earth-like world. This distinction will become increasingly important as telescopes improve. The James Webb Space Telescope is studying the atmospheres of selected exoplanets, especially larger or favourable targets where atmospheric signals can be detected. Ground-based observatories are becoming more powerful as well. Future telescopes may characterize nearby rocky worlds with increasing precision before humanity attempts to send anything toward another star. Astronomy may be able to tell us far more about what is there. Computer simulations add another layer. Researchers can model spacecraft trajectories, dust impacts, radiation environments, fusion concepts, sail dynamics, closed ecosystems, and population genetics without building an entire interstellar vehicle. Simulation does not prove that a mission will work. Its value is different. It identifies failure modes. A proposed sail may become unstable under a laser beam. A shielding design may require too much mass. A generation ship population may become genetically vulnerable under certain assumptions. A thermal system may be unable to reject enough heat. Discovering such problems mathematically or computationally is far cheaper than discovering them after launch. This gradual accumulation of knowledge is how difficult technologies usually emerge. There was no single invention that created modern aviation. Aerodynamics, engines, materials, navigation Weather forecasting, manufacturing, and control systems matured together. Interstellar travel, if it ever becomes practical, may develop in the same way, not through one miraculous engine, but through convergence, better energy systems, better propulsion, better autonomous repair, better radiation protection, better ecological recycling, better knowledge of nearby stars, better understanding of human biology away from Earth, at present. However, these pieces are at radically different levels of maturity. Long-duration robotic missions are real. Human life support lasting months is real. Solar sailing is real. Nuclear fission is real. Fusion propulsion is not. Human artificial gravity habitats are not. Multi-generational closed ecosystems are not. Relativistic spacecraft shielding has not been demonstrated. Human interstellar flight therefore remains far beyond existing capability. But modern astronomy is doing something just as important as building technology. It is revealing the environment into which that technology would travel. Voyager has shown that interstellar space is not an abstract emptiness. Telescopes show that neighboring stars possess planets. Measurements reveal magnetic fields, gas clouds, energetic particles, and structures between stellar systems. The ocean is beginning to acquire weather, and as our maps improve, another uncertainty emerges. We have spent much of this journey discussing how a spacecraft might survive itself, but survival also depends on what lies outside its walls. Between the Sun and the nearest stars stretches a medium we have sampled directly in only a few places. It is thin enough to look like nothing, yet across light years, even almost nothing can matter. Interstellar space is often described as a vacuum. For most practical purposes, that description is reasonable. The density of matter between stars is extraordinarily low compared with anything experienced at Earth's surface. A small volume of air around you contains vastly more particles than an equivalent volume in the space separating the Sun from its neighbours. But vacuum does not mean nothing. The darkness between stars contains matter, radiation, and magnetic structure. And because an interstellar spacecraft would spend years or centuries moving through it, even a remarkably thin environment becomes important. The Sun currently travels through a region known as the local interstellar cloud. This is a diffuse concentration of material within the larger neighbourhood surrounding the solar system. It contains mostly hydrogen and helium, some of it neutral and some ionized, along with trace heavier elements and dust. The cloud is extremely tenuous. A spacecraft would not experience anything resembling aerodynamic drag in Earth's atmosphere. There would be no wind against a window, no sound, no visible fog. Yet the particles are real. We know this partly because the heliosphere responds to them. The solar wind expands outward until it meets the surrounding interstellar medium. The pressure, density, magnetic field, and motion of that medium help shape the heliosphere's outer regions. Voyager's measurements beyond the heliopause therefore provide something unprecedented. They allow us to sample local interstellar conditions directly. Before Voyager, much of our understanding came from astronomical observations and models. Now instruments built on Earth are physically moving through material that did not originate inside the heliosphere. The environment is not uniform. This is one of the first complications. Interstellar matter is distributed into regions with different temperatures, densities, ionization states, and motions. Some clouds are relatively cool and dense by interstellar standards. Other regions contain hot, highly rarefied plasma. The Sun's immediate galactic neighbourhood appears to lie within a much larger structure often called the local bubble. This cavity extends for hundreds of light years and contains very low-density material. It was probably shaped by ancient supernova explosions and the activity of massive stars over millions of years. The solar system, therefore, does not travel through a featureless background. It moves through the changing geography of the galaxy. Over geological time, the Sun may enter different interstellar environments. A denser cloud could compress the heliosphere. A more tenuous environment could allow it to expand. Researchers investigate how such changes might influence the flux of cosmic rays reaching planetary environments. Though the consequences depend on many factors and remain an active area of study, for an interstellar traveller, this matters because a route to another star would pass through regions whose detailed structure may not be completely known before departure. Astronomers can study absorption lines in starlight to infer the material lying between us and nearby stars. When light passes through gas, atoms and ions absorb specific wavelengths. Those patterns reveal composition, motion, and other physical properties. In this way, the apparently empty path toward a star can be studied indirectly. Dust is more elusive. Interstellar dust grains are tiny solid particles composed of materials such as silicates and carbon-rich compounds. They represent only a small fraction of the mass of the interstellar medium. But at high spacecraft velocity, their size can be deceptive. A grain too small to notice in ordinary circumstances can become dangerous when the relative collision speed reaches thousands or tens of thousands of kilometers per second. Fortunately, space is sparse. A spacecraft would not be continuously struck by large grains. The engineering challenge comes from probabilities accumulated across enormous distances. A mission designer would need to understand not merely the average density of dust, but the distribution of grain sizes. Rare events matter when the consequences are severe. This creates an unusual problem for astronomy. Small grains can be studied statistically. Large objects are easier to detect individually if they are sufficiently bright or nearby. But intermediate hazards along a narrow interstellar trajectory could be difficult to catalogue completely. No telescope can guarantee that every particle along a path several light-years long has been identified. The spacecraft would therefore need resilience against uncertainty. Magnetic fields add another invisible structure. The galaxy contains magnetic fields extending through interstellar space. They are weak compared with familiar magnets on Earth, but over astronomical scales they influence charged particles and plasma. The local interstellar magnetic field interacts with the heliosphere and affects the behavior of cosmic rays. For certain proposed propulsion systems, magnetic fields might even become useful. Magnetic sails have been suggested as a way of interacting with charged particles during deceleration, rather than carrying all the propellant required to stop. A spacecraft might deploy a large magnetic structure and transfer momentum to the surrounding plasma. Whether such a system could achieve practical performance for a real interstellar mission depends on engineering assumptions that remain uncertain. Still, the concept illustrates a broader point. The interstellar medium is not merely an obstacle. It could become part of the transportation system. There have even been proposals for spacecraft that collect interstellar hydrogen and use it as fuel. Most famously the Bussard ramjet concept. In its idealized form, an enormous electromagnetic scoop would gather hydrogen while the spacecraft moved through space, feeding fusion reactions and reducing the need to carry all fuel from the beginning. The concept is elegant. Its practical difficulties are formidable. Interstellar hydrogen is extremely sparse. Collecting and compressing it is challenging. Drag from the collection process can work against acceleration. Fusion of readily available proton-based fuel is much harder to exploit than some alternative fusion reactions. For these reasons, the classic ramjet remains speculative, but it demonstrates how our understanding of interstellar space changes the kinds of journeys we can consider. Then there are cosmic rays. These particles can carry extraordinary energies. Some originate from supernova remnants and other energetic processes in the galaxy. Others come from even farther away, because they are electrically charged. Magnetic fields alter their trajectories, making their exact origins difficult to trace for a spacecraft. They represent a persistent radiation environment that cannot simply be avoided by choosing a clear path. Shielding helps, but extremely energetic particles can produce secondary radiation when they strike spacecraft materials. Designing protection therefore involves more than placing a thick wall around the crew. Material composition and geometry matter. An interstellar vessel might place its most heavily occupied areas deep inside the spacecraft, surrounded by water, supplies, structural material, and dedicated shielding. The external environment would shape the internal architecture, and yet our knowledge remains incomplete. Voyager 1 and Voyager 2 provide measurements along only two paths. They are extraordinary paths, but the heliosphere is vast. The space between stars is vastly larger. Future interstellar probes may discover local structures that current observations only hint at. This is not unusual in exploration. Maps improve when travelers enter the territory. But interstellar travel presents a peculiar difficulty. A traveler moving at a significant fraction of light speed has limited time to respond to surprises ahead. The faster the vehicle, the farther forward its sensors must effectively think. A hazard detected too late cannot simply be avoided with a sharp turn. Velocity gives distance a new meaning. The interstellar ocean is therefore neither empty nor crowded. It occupies a strange middle ground, thin enough that stars can shine through it, dense enough to shape heliospheres, quiet enough that Voyager can drift through it for millennia, yet potentially energetic enough to damage a vehicle crossing it at extreme speed. And this brings us toward the true frontier. We can propose engines, we can design shields, we can model habitats, we can study the space between stars. But a human interstellar mission would require every one of these systems to succeed together. The hardest problem may not be any single barrier. It may be the need to cross all of them at once. Engineering problems are often solved by isolation. A bridge can be studied as a problem of structure and materials. A reactor can be studied as a problem of energy and heat. A spacecraft trajectory can be calculated from gravity, velocity, and time. But a human interstellar mission refuses to remain divided into separate problems. Every solution touches another constraint. Make the shielding thicker, and the spacecraft becomes heavier. Make the spacecraft heavier, and propulsion becomes harder. Increase propulsion power, and more waste heat must be removed. Add larger radiators, and the vehicle gains more structure exposed to interstellar impacts. Travel more slowly, and propulsion becomes easier, but life support must operate longer. Travel faster, and the voyage becomes shorter, but collisions become more energetic. Increase the crew to improve genetic and social resilience, and the habitat must grow. Reduce the crew to save mass, and the biological and cultural risks increase. The frontier is therefore not one impossible component, it is integration. This is a familiar problem in complex engineering. A technology can work perfectly in isolation, and still fail when incorporated into a larger system. A powerful engine is useless if its heat destroys the vehicle. An excellent life support system is insufficient if its filters require materials the ship cannot manufacture. A radiation shield is not practical if accelerating its mass requires an unrealistic amount of energy. Interstellar travel amplifies this system's problem, because the vehicle cannot depend on a nearby industrial civilization after departure. On Earth, complexity is supported by networks. A modern aircraft may contain millions of parts, but the aircraft itself does not manufacture those parts. Factories do. Those factories depend on mines, power stations, transportation systems, computer networks, specialized tools, chemical industries, and workers trained by educational institutions. The finished aircraft sits at the end of an enormous technological tree. A generation ship would have to carry enough of that tree with it to remain functional. This is sometimes overlooked when discussions focus on whether a particular engine could theoretically reach another star. Reaching cruise velocity is only one moment in the life of the mission. The spacecraft must survive construction, launch, acceleration, cruise, maintenance, potential collisions, biological emergencies, deceleration, arrival, and perhaps settlement. A mission lasting centuries would also face an enemy that rarely appears in idealized diagrams. Ordinary aging, materials change over time, metals can fatigue, polymers degrade, lubricants break down, radiation damages electronics, microscopic cracks can grow, seals lose performance, sensors drift. Corrosion can occur wherever reactive materials and fluids interact. Biological systems evolve, software accumulates modifications. Even on Earth, where replacement parts and technicians are readily available, maintaining complex infrastructure for centuries is difficult. There are buildings that have survived for 1,000 years. There are mechanical clocks that have operated for centuries with maintenance. But no technological system remotely comparable to an interstellar spacecraft has operated continuously for such periods. Longevity therefore cannot mean building components that never fail. Failure is inevitable. The ship must be designed around repair. That leads to self-sufficiency. Suppose an essential pump fails 180 years after departure. The crew has the design files, but the original spare pumps were used decades earlier. Can they manufacture another? If so, can they produce the alloys? Can they create the bearings? Can they manufacture the electronics that control it? Can they test the replacements safely? And can the tools required for all these processes themselves be maintained? A truly autonomous spacecraft may need manufacturing capabilities far beyond today's three-dimensional printers. It might require a compact industrial civilization. Raw materials would also need to circulate. A broken component is not merely waste. It is a source of atoms. Metals could be recovered. Water could be purified. Carbon compounds could be reused. Nutrients could return to agriculture. The distinction between machine maintenance and ecology begins to blur. Both depend on cycles. Earth survives partly because it is not a disposable system. Water cycles, carbon cycles, nitrogen cycles. Elements move repeatedly through atmosphere. Oceans, rocks, organisms, and soils. A generation ship would need artificial versions of such cycles, not only for biology, but for technology. This requirement exposes one of the deepest uncertainties in the entire concept. We do not know how small a self-sustaining technological civilization can be. A city can function because it is connected to a planet. A remote island can function because ships and aircraft bring supplies. A space station functions because Earth continually supports it. What happens when every external supply chain is removed? How many people are needed to preserve sufficient expertise? How much industrial equipment? How many tons of raw material? How many independent copies of essential systems? How much agricultural area? The answer may determine whether a generation ship is merely enormous, or so enormous that propulsion becomes unrealistic. Then there is uncertainty itself. Engineering normally relies on testing. Aircraft wings are stressed repeatedly. Engines run for thousands of hours. Spacecraft components are exposed to vacuum, vibration, radiation, and temperature extremes before launch. But no laboratory can operate a full-generation ship for 400 years before declaring it safe. Some failure modes would appear only after timescales longer than the lives of the designers. Simulation can help. Accelerated aging tests can help. Redundancy can help. Autonomous monitoring can help. But none eliminates the unknown. This is why the first genuine interstellar missions are far more likely to be robotic. Machines allow civilization to learn without solving every biological and social problem simultaneously. A tiny probe could test high-speed propulsion. A larger probe could study dust impacts. Another might attempt deceleration near a neighboring star. Successive generations of machines could gradually transform speculation into measured experience. Human travel would likely come much later, if it comes at all. And even robotic missions face a severe requirement: reliability across decades without intervention. Artificial intelligence and autonomous systems could help future probes diagnose faults and make decisions when Earth is years away by radio. But autonomy creates its own engineering questions. A system capable of repairing itself must recognize failures accurately. It must possess tools and materials. It must distinguish unexpected conditions from sensor errors. And its decision-making architecture must remain reliable despite radiation damage and hardware degradation. The frontier of interstellar travel is therefore not located at one particular technology. It lies where many disciplines meet. Propulsion touches energy. Energy touches heat. Heat touches materials. Materials touch manufacturing. Manufacturing touches resources. Resources touch population size. Population size touches ecology. Ecology touches medicine. Medicine touches social organization. Social organization touches the purpose of the mission itself. The chain keeps expanding. This may explain why interstellar travel remains distant despite enormous advances in individual fields. Humanity has become exceptionally good at solving specialized problems. Crossing the stars may require us to build a system in which almost nothing can be treated as separate. And even if that system could be constructed, the distance between stars would impose one constraint that engineering cannot remove. Earth would no longer be present in real time. A civilization aboard the ship would make decisions alone. Its messages would travel at the speed of light, and no faster. At interstellar distances, that delay changes more than communication. It changes what it means for two human communities to belong to the same civilization. For most of human history, distance meant delay. A message carried on foot might take days. A letter crossing an ocean could take months. Governments made decisions without knowing what had recently happened in distant territories. Families waited for news that was already old by the time it arrived. Technology gradually compressed those delays. The telegraph separated communication from physical transportation. Radio crossed oceans almost instantly. Satellites created global networks in which events on opposite sides of Earth can be observed at nearly the same moment. Modern civilization has become accustomed to a planet where information moves so quickly that distance often feels socially irrelevant. Interstellar space reverses that trend, not because our communication technology becomes primitive, but because it reaches a boundary that engineering cannot simply improve away. Light has a finite speed. According to special relativity, information cannot be transmitted through ordinary space faster than light. No more powerful antenna changes this. No better computer changes it. The limitation is woven into the causal structure of the universe as we currently understand it. Between Earth and the Moon, the delay is small. A radio signal takes a little over a second to cross the distance one way. During the Apollo missions, this delay was noticeable but manageable. Mars is different. Depending on the relative positions of Earth and Mars, one-way communication can require several minutes to more than 20 minutes. A rover on Mars therefore cannot be driven like a remote-controlled car. Commands must be planned. The machine must possess some autonomy. By the time we reach the outer solar system, delays are measured in hours. Voyager receives instructions long after they are transmitted, and Earth waits many additional hours for confirmation. But Alpha Centauri changes the scale completely. A message sent from Earth to Proxima Centauri would take about 4.24 years to arrive. A reply sent immediately would take another 4.24 years to return. A simple question and answer would require more than 8 years. That is not conversation. It is correspondence between different moments in history. Suppose a human settlement eventually existed there. A child could be born after Earth transmitted a message and be attending school before the reply returned. Political administrations might change between question and answer. Scientific discoveries could occur on one world and remain unknown on the other for years. There would be no shared present in the ordinary social sense. Each community would see the other as it had been. This effect becomes more severe with distance. At 10 light years, a round-trip exchange requires at least 20 years. At 50 light years, a question sent by a young adult might receive its response when that person was approaching old age. At hundreds of light years, meaningful two-way interaction becomes intergenerational. The galaxy does not prohibit communication. It stretches it until communication becomes archaeology of the recent past. This would have profound consequences for any civilization that spread beyond the solar system. A central government on Earth could not control a distant colony in real time. Orders would arrive years after the circumstances that motivated them. Local leaders would have to respond to emergencies independently. Economic systems based on rapid exchange would be impossible between stars. Physical trade would be even slower. Information might remain valuable enough to exchange. Scientific discoveries, art, historical records, engineering designs, genetic information. But physical goods would require spacecraft journeys lasting decades or longer. An interstellar civilization might therefore be connected primarily by knowledge rather than commerce. Even knowledge would diverge. Consider two human societies separated by 10 light years. Each continues developing technology. Each creates new art, institutions, language, and customs. They exchange information, but every message reflects the sender's society 10 years earlier. The receiving civilization responds to a version of the other that no longer exists. Over centuries, their cultures could drift apart even if communication never stopped. Language provides a familiar example. Human languages can change significantly over several centuries even when speakers remain connected. Separate communities evolve faster in different directions. Interstellar settlements would experience separation more complete than any ocean on Earth. Their environments might also differ. A colony on a planet with lower gravity, different day length, unfamiliar seasons, or artificial habitats would develop routines adapted to those conditions. If biological adaptation or deliberate genetic modification ever occurred, the divergence could become physical as well as cultural. Though predicting such developments would move beyond what present science can establish. The important point requires no speculation. Distance creates autonomy. A human community several light years away must be capable of surviving without immediate help from Earth. That autonomy begins before arrival. A generation ship is already an independent society in practical terms. Once it has travelled far enough, turning around may be unrealistic. Earth cannot repair its machinery. Earth cannot send emergency medicine in time. Earth cannot enforce decisions. The people aboard must govern themselves. This creates a curious possibility. The moment humanity becomes capable of establishing communities around other stars may also be the moment the idea of a single human civilization begins to weaken. Not because the communities become hostile. They may remain deeply connected by history and affection, but physics denies them simultaneity at the social scale. There can be no galactic capital issuing immediate instructions across hundreds of light years, no live debate involving citizens scattered among distant stars, no emergency response arriving from another system in hours. Popular stories often portray interstellar civilizations as enlarged versions of terrestrial nations. Real relativity suggests something more fragmented. A network of islands. Each island sees delayed images of the others. Each must survive largely on its own. The nearest stars are close enough that cultural exchange might still be meaningful. A 4-year delay is profound, but not incomprehensible. Human institutions already pursue projects lasting decades. Scientific collaborations can extend across generations. A patient civilization might maintain correspondence with its nearest neighbors, but expansion across greater distances would transform the network. There is another consequence. Travel itself creates separation in time. At velocities far below light speed, travelers simply age during the journey as expected. At sufficiently relativistic speeds, time dilation becomes significant. From Earth's perspective, the spacecraft may require many years to cross a distance, while less time passes for those aboard. This effect is real and experimentally confirmed. It does not provide faster than light travel. It does mean that very high-speed journeys could alter how travelers experience interstellar distance. But reaching velocities where time dilation becomes dramatic requires extraordinary energies far beyond the propulsion systems we have discussed for near-term concepts. Relativity therefore offers no easy escape. Instead, it deepens the separation between travelers and those who remain behind. A crew might experience a shorter voyage while returning, if return were possible, to an Earth on which much more time had passed. Interstellar expansion would not simply spread humanity through space. It would distribute humanity through different histories. This changes the meaning of the phrase escaping the solar system. Perhaps escape is not primarily crossing a gravitational boundary. Perhaps it occurs when a community travels so far that the solar system can no longer function as its practical center. Beyond that point, Earth remains the birthplace. The Sun remains the ancestral star. Messages may continue to arrive, but survival, government, culture, and daily life belong somewhere else. And if that future ever occurs, it raises a larger question than whether humans can reach another star. What happens when the descendants of Earth no longer share the same present? The far future is unusually difficult territory for science. Physics can tell us what known laws permit. Engineering can estimate what certain technologies might require. Astronomy can describe the stars and planetary systems around us. But no equation can reliably predict what human civilization will be capable of thousands of years from now. The safest way forward is therefore not to predict one future. It is to examine several possible roads and ask which parts are already grounded in evidence. The first road requires no human passengers at all. Robotic interstellar probes are the most plausible first travelers to another star. We already know how to build spacecraft that operate autonomously for years and communicate across billions of kilometers. The difficulty is increasing their velocity by orders of magnitude. Beamed light sails offer one possible route. Instead of building a large spacecraft with an enormous fuel supply, a future civilization could construct a powerful laser system and direct its energy toward a very small reflective sail. The smaller the spacecraft, the easier it is to accelerate. Concepts such as Breakthrough Starshot have explored whether extremely lightweight probes could eventually reach perhaps 20% of light speed at that velocity. A journey to the Alpha Centauri system could take a little over 20 years in simple cruise time terms. That would be remarkable. A spacecraft launched during one stage of a researcher's career might reach another star within the lifetime of people who watched it depart. But such a probe would face severe challenges. The sail must survive an intense laser beam. The spacecraft must remain stable during acceleration. Its electronics must endure decades in space. It must survive collisions with interstellar dust. Navigation must be extraordinarily precise, and after reaching the target, a tiny probe must somehow gather useful observations and transmit them across more than 4 light-years using a very limited power source. These problems are difficult. They are not equivalent to carrying humans. That distinction may shape the next several centuries of exploration. Machines could cross the interstellar ocean long before people do. A second road uses larger robotic probes powered by nuclear energy or, eventually, fusion. A fusion spacecraft might travel more slowly than the most ambitious laser sail concepts while carrying far more scientific equipment. It could potentially decelerate, enter a neighboring stellar system, and study several planets over years. Such a mission remains beyond present technology, because practical fusion propulsion does not yet exist. But it relies on physical processes we know are real. This places it in a very different category from faster-than-light travel. No experimentally supported method currently allows matter or information to outrun light through ordinary space. Ideas involving wormholes or engineered spacetime appear in theoretical physics, but they require conditions or forms of matter and energy that have never been shown to provide a practical transportation system. They cannot responsibly be treated as solutions to human interstellar travel. The roads worth examining are slower. One possibility is suspended animation. If human metabolism could be greatly reduced for long periods, a spacecraft might avoid some of the social problems of a generation ship. The travelers could, in principle, sleep through much of the journey. Nature provides intriguing examples. Many animals enter hibernation or torpor, reducing metabolic activity for extended periods. Medicine can also lower body temperature under controlled circumstances for certain procedures, but humans cannot currently be placed into safe suspended animation for years, much less centuries. Even if future medicine made prolonged torpor possible, the spacecraft would still require maintenance. Someone or something must care for sleeping passengers. Automated systems would need exceptional reliability. Radiation would remain. Cells would still have to survive. The concept could reduce some biological demands, but it would not remove the physics of the journey. Generation ships form another road. They require no revolutionary method of preserving one individual for centuries. Instead, the population continues through reproduction. The journey becomes a sequence of human lives. In principle, this avoids the requirement for extreme speed. A spacecraft traveling at only a small fraction of light speed could eventually reach another star if its society survived long enough. But as we have seen, this solution replaces a propulsion problem with an ecological and civilizational one. A generation ship may be easier for physics than a near-light-speed vessel. It may be harder for everything else. There is another possibility that changes the order of events. Humanity might not attempt true interstellar migration until it has already learned to live permanently away from Earth. Settlements on the Moon, Mars, asteroids, or artificial habitats would not automatically lead to the stars, but they could force us to solve smaller versions of the same problems. Closed-loop life support, radiation protection, artificial ecosystems, independent manufacturing, long-term governance in isolated environments, reproduction beyond Earth. If those capabilities matured over centuries, an interstellar habitat might eventually become less extraordinary. It would still need propulsion, but the civilization building it might already know how to construct artificial worlds. This is perhaps the most important difference between near-future and far-future thinking. We often picture an interstellar spacecraft as an advanced version of a present spacecraft. It may instead resemble a mobile space settlement built by a civilization already accustomed to living in enormous artificial habitats. Its builders might harvest materials from asteroids rather than lifting everything from Earth. Energy might come from vast solar installations near the Sun or from mature nuclear technologies. Construction could occur entirely in space. A vessel weighing millions of tons would be almost absurd to launch from Earth's surface. It is less absurd if its raw materials never begin on Earth. This does not make the project easy. It changes which constraints dominate. There are also destinations other than Earth-like planets. A civilization capable of constructing self-sustaining habitats may not need to find another Earth. It could live in artificial environments within another stellar system. Asteroids and small moons might provide raw materials. A destination star could provide energy. The search for a perfect terrestrial planet would become less important than the search for accessible matter and stable energy. This possibility reveals a subtle reversal. To escape the solar system, humanity may first need to become extraordinarily good at living inside it. The outer planets, moons, asteroids, and artificial habitats could become laboratories for the technologies required between stars. If we cannot maintain a closed settlement a few light minutes from Earth, maintaining one several light years away would be difficult to justify. The solar system may therefore be less a prison than a training ground. Its enormous distances already challenge communication. Its planets and moons offer hostile environments. Its asteroids contain accessible material. Its sunlight provides vast energy close to the sun. Its outer regions provide environments increasingly similar to deep space. Over centuries, a spacefaring civilization could gradually move farther from dependence on Earth without ever making a single decisive leap. And then, perhaps, an interstellar departure would not resemble the heroic launch of one extraordinary vessel. It might be the slow extension of a civilization that had already learned to live between worlds. None of this is guaranteed. Civilizations do not automatically become more technologically capable forever. Economic priorities change. Environmental pressures matter. Political systems rise and fall. Humanity may decide that robotic exploration is sufficient. We may discover that the costs of sending people between stars greatly exceed any practical benefit, or technologies not yet developed may alter the balance in ways we cannot responsibly forecast. Science can identify possibilities. It cannot promise destiny. But one conclusion can already be drawn carefully. There is no single known barrier labelled interstellar travel that physics clearly forbids us from crossing. Instead, there is a sequence of increasingly difficult requirements, and whether humanity ever satisfies them may depend less on one breakthrough than on what kind of civilization exists when the opportunity finally arrives. That returns us to the belief with which we began. Perhaps the stars are not simply destinations waiting for faster ships. Perhaps reaching them requires changing the travellers first. At the beginning of this journey, the solar system seemed to possess a familiar shape. A star at the centre, 8 planets around it, a distant boundary somewhere beyond Neptune, and outside that boundary, the stars. From that perspective, escape appeared to be mainly a problem of transportation. Humanity once crossed oceans with wooden ships. Later, we crossed the atmosphere with rockets, if technology continued improving. It seemed reasonable that another generation of machines would eventually carry us beyond the solar system. The map now looks different. Neptune is not the edge. Beyond it lies the Kuiper Belt, followed by scattered populations of increasingly distant objects. Farther still, the hypothetical Oort cloud may extend tens of thousands of astronomical units from the Sun. Meanwhile, another boundary exists much closer. The heliopause marks the transition between the solar wind and the surrounding interstellar medium. Voyager 1 and Voyager 2 have already crossed it. Humanity has therefore accomplished something that sounds contradictory. Our machines have entered interstellar space while remaining within the much larger gravitational architecture associated with the Sun. The contradiction disappears once we abandon the idea that the solar system has a single wall. It fades outward. Solar light weakens. The solar wind ends. The Sun's gravitational influence becomes increasingly vulnerable to perturbations from passing stars in the galaxy. Eventually, one stellar domain gives way to another. Our spacecraft can cross these regions because escape from the Sun is permitted by ordinary physics. A sufficiently fast object placed on the correct trajectory will not return. Voyager is doing exactly that. So are several other probes. This means the title of our journey contains a deliberate tension. Why humans will never escape the solar system sounds like a statement about an absolute physical prohibition. There is no known prohibition of that kind. Humans are made of matter, and matter can travel on trajectories that leave the Sun. If a spacecraft could support people while following such a trajectory, those people could cross the heliopause. Given enough time, they could travel far beyond the Oort cloud. The real barrier emerges when escape is given a more meaningful definition. Leaving is easy compared with going somewhere. A spacecraft can drift indefinitely through interstellar space. A human mission needs a destination, a survivable travel time, a functioning habitat, energy, shielding, navigation, maintenance, and perhaps a way to stop. The nearest neighbouring star is more than 4 light-years away. That distance transforms engineering. At Voyager-like velocities, the journey lasts tens of thousands of years. At 1% of light speed, it lasts centuries. At 10%, it becomes compatible with a human lifetime, but the energy requirements and collision hazards become much more severe. Every attempt to solve the problem reveals another layer. Faster propulsion shortens exposure time but demands more energy. More shielding protects the crew but increases mass. A larger population improves some forms of resilience but requires a larger habitat. A longer journey reduces the required speed but demands extraordinary reliability. There is no obvious point at which one invention dissolves the entire problem. This distinguishes interstellar travel from many earlier frontiers. Crossing an ocean required ships capable of surviving the ocean. Crossing interstellar space may require a vessel capable of replacing much of the planetary system that normally keeps its passengers alive. Earth provides life support almost invisibly. A spacecraft must make every function explicit. Air becomes machinery. Water becomes plumbing and chemistry. Food becomes agriculture. Gravity may become rotation. Radiation protection becomes structural mass. Waste becomes raw material. Medicine becomes permanent infrastructure. Manufacturing becomes survival. And if the voyage lasts longer than a human life, culture itself becomes part of the vehicle. The generation ship showed us where this reasoning leads. The passengers cease to be passengers. The vessel becomes their world. Its population must maintain knowledge, machinery, ecology, and social institutions across generations. People born aboard would inherit a destination chosen before they existed. Whether such a society could remain stable is not something astronomy can answer. We have no experimental precedent. Perhaps this is the most important uncertainty of all. We understand the physics of stars better than we understand the behavior of a civilization isolated for centuries. Yet our exploration of the solar system is slowly addressing pieces of the larger challenge. Voyager demonstrates longevity. New Horizons demonstrates navigation across billions of kilometers. Solar sails demonstrate propulsion without conventional fuel. Nuclear systems provide power where sunlight is weak. Space stations test recycling and long-duration human habitation. Astronomy discovers planets around nearby stars. Computer models expose weaknesses in proposed spacecraft before they are built. None of these achievements creates an interstellar civilization. Together, however, they replace a vague dream with a more precise set of questions. That is often what scientific progress looks like. Knowledge does not always make a problem easier. Sometimes it reveals why the problem was harder than we thought. A century ago, one might have imagined that reaching the stars required only a sufficiently powerful rocket. Now we can see the intertwined constraints of energy: relativistic velocity, radiation, interstellar dust, thermal management, ecology, genetics, manufacturing, autonomy, and communication delay. The stars have not moved farther away. Our understanding of the journey has become deeper. There is another change in perspective. The solar system no longer looks like something humanity should be impatient to escape. It contains extraordinary room for expansion. The energy of the sun, the resources of asteroids, the surfaces of moons and planets, billions of small bodies, vast regions where artificial habitats could, in principle, be constructed. Even if humans never reach another star, the physical territory available within the sun's domain is immense compared with everything our species has occupied so far. And if humans eventually do reach another star, mastering this territory may be the preparation that makes the journey possible. The civilization capable of building an interstellar vessel may not be a civilization confined to Earth. It may already inhabit many places. Its people may consider closed habitats ordinary. Its industries may operate in space. Its energy systems may function on scales difficult for us to contemplate. Its machines may repair themselves. Its settlements may already survive without immediate support from Earth. For such a civilization, crossing several light years would remain difficult. But difficulty is relative to capability. This is why predictions about what humanity will never accomplish deserve caution. We cannot know the technologies, institutions, or priorities of people living thousands of years from now. We can only identify what present knowledge tells us. Nothing in established physics offers an easy road to the stars. Nothing currently available to humanity can carry a self-sustaining human civilization to another stellar system on a practical timescale. And no experimentally supported shortcut allows us to ignore the distance. That is a much more interesting conclusion than impossibility. It leaves the future open while respecting the severity of the problem. The question has changed. We began by asking whether humans could escape the solar system. We are ending with something more difficult. What would humans have to become before the word escape stopped describing the journey at all? Perhaps the first people to cross the true gulf between stars would not think of themselves as leaving a home behind. They might belong to a civilization for which home had already ceased to mean one planet, and from their perspective, the solar system might not appear as the prison their ancestors once feared. It might appear as the place where humanity slowly learned how to live without a shore. There is only one step left in our journey. Not another engine, not another equation, not another proposed spacecraft, only the quiet distance itself, and what it means for a species that can see the stars long before it can reach them. There is a peculiar stillness at the edge of the solar system. Not silence in the ordinary sense, because sound has little meaning in such thin space. Rather, it is a stillness of scale. The sun remains behind, still brighter than every other star, yet no longer large enough to resemble the blazing disk seen from Earth. The planets have disappeared into its direction. Their enormous orbits, their moons, their rings, their storms and oceans have contracted into a region too small for the unaided eye to separate. Ahead lies almost nothing visible, and somewhere inside that darkness are other suns. For thousands of years, human beings looked upward and treated the stars as part of the distant sky. We learned their patterns. We named them. We used them to navigate oceans. Eventually, astronomy revealed what they really were. The points of light were suns. Many possessed planets. The darkness between them was measurable. And once their distances became known, an old human instinct naturally followed. If those are places, perhaps one day we will go there. Nothing in our journey has completely removed that possibility. There is no invisible wall surrounding the solar system. There is no known boundary that living matter is forbidden to cross. Voyager has already carried human technology through the heliopause. Its trajectory continues outward. Other spacecraft are also leaving the sun on paths from which they will not return. In this limited sense, escape is already happening, but the machines drifting outward remind us how different motion is from migration. Voyager needs almost nothing from the universe now. It does not need a destination. It does not need to preserve a society. When its final instruments fall silent, the spacecraft can continue without knowing that anything has changed. It may travel for millions of years. Humans cannot travel that way. Wherever we go, we carry a narrow set of conditions with us. Temperature, pressure, water, air, food, protection, gravity, or something capable of reproducing its effects. We carry biology shaped by billions of years on Earth. And behind that biology travels something even more difficult to engineer. Culture, memory, language, purpose. A vessel carrying people to another star would therefore carry far more than passengers. It would carry fragments of a world. Perhaps that is why interstellar distance feels so different from the distances our ancestors crossed. An ocean separates shores. The space between stars separates entire environments. There may be no island halfway to Alpha Centauri where a damaged ship can stop. No harbour, no settlement, no source of replacement parts. For most of the journey there is only the spacecraft, the people within it, and an expanding sphere of radio signals connecting them imperfectly to the world behind. At first, Earth would answer quickly enough. Then the pauses would lengthen. Hours would become days. Days would become months. Eventually, years would separate a question from its reply. Earth would still exist, but it would no longer exist for the travellers in the immediate present. They would know only the Earth whose light and messages had already crossed the distance. The same would be true in reverse. Those remaining near the sun would watch an increasingly delayed version of the travellers. Two human communities could remain connected while never again sharing the same moment. There is something peaceful in recognizing this limitation. The universe does not appear to have arranged itself around our desire to travel conveniently through it. Its scales emerge from processes vastly older than humanity. Stars formed where gravity gathered matter. Galaxies grew. Planetary systems condensed from disks. The distances between them were not designed as roads. We are the ones who look across those distances and wonder whether roads can be built. Perhaps they can. Fusion may one day become a practical source of spacecraft propulsion. Beam sails may send tiny probes toward neighboring stars. Artificial habitats may become increasingly independent. Closed ecosystems may improve. Space manufacturing may allow structures to be built that could never be launched from Earth. Centuries of exploration inside the solar system may teach future civilizations lessons we cannot yet anticipate. Or perhaps human beings will remain close to the sun while our machines travel farther. There would be no failure in that future. A robotic probe reaching another star would still extend human knowledge across a distance that once seemed beyond measurement. Information returning from such a mission could reveal planets, atmospheres, magnetic fields, moons, and landscapes beneath another sun. Exploration does not require that every frontier eventually become a place of human settlement. The universe can be known without being occupied, and perhaps this is the quieter lesson hidden inside the idea of escape. We often describe Earth, and sometimes the solar system, as something to leave, but the farther outward we look, the more extraordinary our position becomes. We live beside a stable star, on a rocky world with liquid oceans, inside an atmosphere we can breathe without machinery, within a biosphere whose complexity no spacecraft designer knows how to reproduce completely. Every forest is a life support system more intricate than anything we have built. Every river participates in a planetary recycling network. Every breath depends on processes extending through organisms, oceans, rocks, atmosphere, and sunlight. Spaceflight teaches us the value of these ordinary things by forcing us to manufacture pale versions of them. Perhaps a civilization capable of crossing the stars would understand its home more deeply because of that difficulty. It would know that carrying life between stars is not simply a matter of moving bodies through space. It is the movement of an ecology, a history, a continuity stretching back to the first life on Earth. And so we return to the assumption with which the journey quietly began. Human history appears to be a history of disappearing boundaries. We crossed the horizon, we crossed the oceans, we crossed the atmosphere, we reached another world. From that sequence, the stars seem like the inevitable next step. But perhaps history does not promise inevitability. Perhaps it only gives us questions. The stars are physically real destinations, yet they are separated from us by distances so great that reaching them may demand more than faster transportation. It may require technologies we have not developed, habitats we have not tested, societies we have never created, and patience measured not in missions, but in generations. For now, the solar system remains our only known home. Not merely Earth, the entire immense region around our sun is the first cosmic landscape humanity has begun to explore. Voyager moves through its distant boundary. New Horizons travels deeper into its outer darkness. Other probes circle planets, cross asteroid belts, approach the sun, and search distant worlds from telescopes near Earth and far beyond it. Slowly, our understanding expands farther than our bodies can travel. Perhaps that has always been the beginning of exploration. First we see, then we measure, then we understand enough to recognize how much remains unknown. Far beyond the planets, the sun eventually becomes one star among many. Beyond it waits the interstellar ocean, crossed today only by light, particles, and a handful of small machines moving outward from their birthplace. Whether human beings will ever follow them remains unanswered, and somewhere in the darkness, more than 4 years away even at the speed of light, another star continues burning. Around it move worlds we're only beginning to understand. The distance between us is real. The laws of physics are real. So are the limits of everything we can presently build. But the future has not yet become evidence. And perhaps the most scientifically faithful place to end is therefore not with a prediction, but with the same uncertainty that has accompanied humanity whenever the known world reached its horizon, when the sun has become only another star behind us. What kind of beings, if any, will be looking back?